Hello children, let us start third chapter, and that is complex numbers. In our previous classes, we have studied number systems. Number systems story starts with natural numbers. Counting numbers such as 1, 2, 3, 4 and so on up to infinity are called natural numbers. If we include 0 in this set, it becomes a set of whole numbers. That means 0, 1, 2, 3, 4 and so on up to infinity. If we include numbers on the other side of 0 as well, they become a set of integers. That means numbers between minus infinity to plus infinity, such as minus 2, minus 1, 0, 1, 2 are called integers. Then comes real numbers. Real number set consists of two types of numbers, rational numbers and irrational numbers. Rational numbers are those numbers which can be written in the form p by q, where p and q are integers and q is not equal to 0. For example, 1 by 2, 1 by minus 2, minus 1 by 2, they are called rational numbers. Irrational numbers are those numbers which cannot be written in the form p by q, where p and q are integers and q is not equal to 0. For example, root 2, root 3, root 5, root 7, they are irrational numbers. On top of the stack comes imaginary numbers or complex numbers, which we will study in detail in this chapter. Complex numbers are defined as the expressions of the form a plus ib, where a and b are real and I is equal to under root minus 1. It is denoted by z. So z is equal to a plus ib. A is called the real part and written as A is equal to REZ. RE is short form of real. B is called imaginary part and written as B is equal to IMZ. IM is short form of imaginary. Euler was the first mathematician to introduce the symbol I, which is iota, for the square root of minus 1. He also called this symbol as the imaginary unit. In z is equal to a plus ib, this is real part and this is imaginary part. So if b is equal to 0, z is equal to a. So the complex number z will be called as purely real. And if a is equal to 0, z is equal to ib. So the complex number z will be called as purely imaginary. 0 is both purely real and purely imaginary, but not imaginary or complex number. I is equal to under root minus 1. We will find out the values of I square, I cube and I to power 4. I square is equal to under root minus 1 whole square, and that is equal to minus 1. I cube can be written as I square into I. Value of I square is equal to minus 1. So it becomes minus 1 into I, and that is equal to minus I. I to power 4 can be written as I square whole square. Value of I square is equal to minus 1. So that becomes minus 1 whole square, and that is equal to 1. You need to keep these 4 values in your mind. In general, I to power 4n is equal to 1. I to power 4n plus 1 is equal to I to power 4n plus 2 is equal to minus 1, and I to power 4n plus 3 is equal to minus I, where n is integer. Now let us understand complex plane. In number systems, natural numbers, whole numbers, integers, and real numbers are represented on number line. But complex numbers cannot be represented on number line. They are represented in complex plane, which is very similar to 2D Cartesian coordinate plane. In place of x-axis, it is real axis, and in place of y-axis, it is imaginary axis. This is origin. Suppose there is a point A which represents a complex number z. Its real part is A and imaginary part is B. So point A can be represented by ordered pair A, B, and complex number z can be represented by z is equal to A plus IB, where A is equal to real part of z and B is equal to imaginary part of z. All the numbers which lie on real axis are called purely real, and all those numbers which lie on imaginary axis will be called as purely imaginary. This is Argand diagram. Now let us see equality and inequality of complex numbers. First we will see equality of complex numbers. Two complex numbers Z1 and Z2 are equal if and only if their real parts are equal and their imaginary parts are equal. Suppose Z1 is equal to A1 plus IB1 and Z2 is equal to A2 plus IB2. So Z1 is equal to Z2 if and only if A1 is equal to A2 and B1 is equal to B2. Inequality of complex numbers. Inequality of complex numbers is not defined. Suppose Z1 and Z2 are two complex numbers. If we say Z1 is greater than Z2, there is no way to verify that. For example, let's say Z1 is equal to 3 plus I and Z2 is equal to 1 plus 2I. So if Z1 is greater than Z2, that means 3 plus I is greater than 1 plus 2I. If we simplify this, we get 2 minus I is greater than 0 or I is less than 2, which is meaningless because we know I is equal to under root minus 1. Now let us solve a couple of questions based on what we have studied so far. First question, evaluate the following. Part A, I to power 135. Part B, I to power minus 999. Part A, I to power 135. We know that I to power 4 is equal to 1. So we will divide the given power by 4. We get 33 as quotient and 3 as remainder. So this can be rewritten as I to power 4 to power 33 into I to power 3. I to power 4 is equal to 1 and I cube is equal to minus I. 1 to power 33 is equal to 1. So it becomes 1 into minus I and that is equal to minus I. Part B, I to power minus 999. Minus 999 can be written as minus 1000 plus 1. So this can be written as I to power minus 1000 into I. Minus 1000 can be rewritten as 4 into minus 250. So it becomes I to power 4 to power minus 250 into I. I to power 4 is equal to 1 and 1 to power any number is equal to 1. So it becomes 1 into I and that is equal to I. Second question, show that part A, I to power 18 plus 1 by I to power 24 whole to power 3 is equal to 0. Part B, I to power n plus I to power n plus 1 plus I to power n plus 2 plus I to power n plus 3 is equal to 0. Part A, LHS is equal to I to power 18 plus 1 by I to power 24 whole to power 3. We will divide 18 by 4. So 18 can be rewritten as 4 into 4 plus 2. 1 by I can be rewritten as I upon I square. Multiply both numerator and denominator by I. This can be rewritten as I to power 4 to power 4 into I square. I square is equal to minus 1. So first term can be simplified as I to power 4 is equal to 1 and I square is equal to minus 1. So first term comes as minus 1. Second term, I upon minus 1, that is equal to minus I. Minus I can be rewritten as minus 1 into I. Now we will separate both. Minus 1 to power 24 into I to power 24. Minus 1 to even power, which will become plus 1. And I to power 24 can be rewritten as I to power 4 to power 6. I to power 4 is equal to 1. So second term becomes plus 1. Now minus 1 and plus 1 will cancel each other. So the answer is 0, which is right hand side. Part B, LHS is equal to I to power n plus I to power n plus 1 plus I to power n plus 2 plus I to power n plus 3. We will take I to power n common in all the terms. So in bracket we get 1 plus I square plus I cube. We know that I square is equal to minus 1 and I cube is equal to minus I. Plus 1 and minus 1 will cancel each other. Plus I and minus I will cancel each other. So in bracket we get 0. I to power n into 0 is equal to 0, which is right hand side. Let us see algebraic operations on complex numbers. We will see addition, subtraction, multiplication, division of complex numbers and their associated properties. First, addition. Suppose Z1 and Z2 are two complex numbers such that Z1 is equal to A1 plus IB1 and Z2 is equal to A2 plus IB2. So Z1 plus Z2 is equal to A1 plus A2 plus I into B1 plus B2. This is real part and this is imaginary part. It is clear from here that real of Z1 plus Z2 is equal to real of Z1 plus real of Z2. and imaginary of z1 plus z2 is equal to imaginary of z1 plus imaginary of z2. Let us see properties of addition of complex numbers as we have been doing in our previous classes for other types of numbers in number systems. First property, closure property. If z1 and z2 are two complex numbers, then z1 plus z2 will also be a complex number. It is clear from here. Second property, commutative property. Whether you add z2 to z1 or z1 to z2, result will be the same. Third property, associative property. Suppose z1, z2 and z3 are three complex numbers, then they can be added together in any order. First add z1 to z2 and the result to z3, or first add z2 to z3 and the result to z1. Outcome will be the same. Fourth property, additive identity. Complex number 0 is called additive identity for complex numbers. Complex number 0 means its real as well as imaginary part is 0. When you add 0 to any complex number, you will get the same complex number. Fifth property, additive inverse. If a complex number is z, then minus z is called as its additive inverse. Or if a complex number is minus z, then plus z is called as its additive inverse, such that when they are added together, result is 0. Now let us see subtraction of one complex number from the other. Suppose z1 and z2 are two complex numbers, such that z1 is equal to a1 plus ib1 and z2 is equal to a2 plus ib2. So minus z2 is equal to minus a2 minus ib2. z1 minus z2 can be written as z1 plus in bracket minus z2. Now we will add these two. So it becomes a1 plus ib1 plus in bracket minus a2 minus ib2. So it can be simplified as a1 minus a2 plus I into b1 minus b2. This is real part and this is imaginary part. It is clear from here that real of z1 minus z2 is equal to real of z1 minus real of z2. And imaginary of z1 minus z2 is equal to imaginary of z1 minus imaginary of z2. Third operation is multiplication of complex numbers. Suppose z1 and z2 are two complex numbers such that z1 is equal to a1 plus ib1 and z2 is equal to a2 plus ib2. So z1 z2 is equal to a1 plus ib1 into a2 plus ib2. This can be simplified as a1 a2 minus b1 b2 plus I into a1 b2 plus a2 b1. This is real part and this is imaginary part. So we can write real of z1 z2 is equal to real z1 into real z2 minus imaginary z1 into imaginary z2. And imaginary z1 z2 is equal to real z1 into imaginary z2 plus real z2 into imaginary z1. Now let us see properties of multiplication of complex numbers. First property is closure property. If z1 and z2 are two complex numbers, then z1 into z2 is also a complex number. We have seen it here. Second property, commutative property. Whether you multiply z2 to z1 or z1 to z2, result will be the same. Third property, associative property. Suppose z1, z2 and z3 are three complex numbers, then they can be multiplied together in any order. First you multiply z1 and z2 and the result to z3, or first you multiply z2 and z3 and the result to z1. Outcome will be the same. Fourth property, multiplicative identity. Complex number 1 is multiplicative identity of complex numbers. 1 can be written as 1 plus 0i, which is purely real. When 1 is multiplied with any complex number, result is same complex number. Fifth property, multiplicative inverse. Multiplicative inverse of a complex number z is equal to 1 by z, so that when they are multiplied together, result is 1. It is denoted by z inverse or 1 by z. Sixth property is distributive property. Suppose z1, z2 and z3 are three complex numbers. Then z1 into in bracket z2 plus z3 is equal to z1 z2 plus z1 z3. This is called distribution over addition of complex numbers. Fourth operation, it is division. The division of a complex number z1 by another non-zero complex number z2 is defined as the multiplication of z1 by the multiplicative inverse of Z2, and it is denoted by Z1 by Z2. So by definition, Z1 by Z2 is equal to Z1 Z2 inverse, or Z1 into 1 by Z2. Let us understand conjugate, modulus and argument. First, conjugate. Suppose Z is equal to A plus IB is a complex number, then conjugate of Z is denoted by Z bar, a small horizontal line over Z, and it is equal to A minus IB. So Z bar is equal to A minus IB. To get the conjugate of any complex number, we just need to change the sign in between real and imaginary parts. If it is plus, make it minus. If it is minus, make it plus. Suppose Z is a complex number denoted by ordered pair A, B. This is A and this is B. So Z is equal to A plus IB. It is in first quadrant. Minus Z is equal to minus A minus IB. Minus A minus B will be in third quadrant. Z bar is equal to A minus IB. We just need to change the sign in between. So plus A minus B. Plus A minus B will be in fourth quadrant. Minus Z bar is equal to minus A plus IB. Minus A plus B will be in second quadrant. Now let us see properties of conjugate. First property, bar of Z bar is equal to Z. Suppose Z is equal to A plus IB, so Z bar is equal to A minus IB. We just need to change the sign in between real and imaginary parts. Bar of Z bar is equal to A plus IB. Again, we need to change this sign. A plus IB is equal to Z. So bar of Z bar is equal to Z. Second property, Z plus Z bar is equal to 2 times real Z. Suppose Z is equal to A plus IB, so Z bar is equal to A minus IB. When we add these two, plus IB and minus IB gets cancelled. A plus A is equal to 2A, and that is equal to 2 times of real Z. So Z plus Z bar is equal to 2 times of real Z. Third property, Z minus Z bar is equal to 2I imaginary Z. When we do Z minus Z bar, it will be A plus IB minus A plus IB. Plus A and minus A gets cancelled. IB plus IB is equal to 2IB, and that is equal to 2I into imaginary Z. So Z minus Z bar is equal to 2I imaginary Z. Fourth property, if Z is equal to Z bar, implies that Z is purely real, or if Z is purely real, implies that Z is equal to Z bar. Let us see how. If Z is equal to Z bar, it means A plus IB is equal to A minus IB. A and A gets cancelled. IB is equal to minus IB. It is possible only when B is equal to 0. That is, imaginary part is 0, or Z is purely real. Fifth property, if Z plus Z bar is equal to 0, implies that Z is purely imaginary. If Z plus Z bar is equal to 0, that means A plus IB plus A minus IB is equal to 0. Plus IB and minus IB gets cancelled. A plus A is equal to 2A. So 2A is equal to 0 means A is equal to 0, or real part is 0. That means Z is purely imaginary. Sixth property, Z bar is equal to real of Z square plus imaginary of Z square. Suppose Z is equal to A plus IB. So Z bar is equal to A minus IB. Z bar is equal to A plus IB into A minus IB, which is equal to A square plus B square. That is real of Z square plus imaginary of Z square. Seventh property, Z1 plus Z2 whole bar is equal to Z1 bar plus Z2 bar. Suppose Z1 is equal to A1 plus IB1 and Z2 is equal to A2 plus IB2. So Z1 bar is equal to A1 minus IB1 and Z2 bar is equal to A2 minus IB2. Z1 plus Z2 whole bar is equal to A1 plus IB1 plus A2 plus IB2 whole bar. We can rearrange the terms to write it in standard form. So it will become A1 plus A2 plus I B1 plus B2. Now we can take conjugate of this complex number. We need to change the sign in between. So it will become A1 plus A2 minus I B1 plus B2. Now we can rearrange the terms again to get A1 minus IB1 plus A2 minus IB2. A1 minus IB1 is equal to Z1 bar and A2 minus IB2 is equal to Z2 bar. So it becomes z1 bar plus z2 bar. So z1 plus z2 whole bar is equal to z1 bar plus z2 bar. Eighth property, z1 minus z2 whole bar is equal to z1 bar minus z2 bar. z1 minus z2 is equal to a1 minus a2 plus I, b1 minus b2. So z1 minus z2 whole bar is equal to a1 minus a2 plus I, b1 minus b2 whole bar. We will take conjugate of this complex number. So we need to change the sign in between. So it will become a1 minus a2 minus I, b1 minus b2. Now we can rearrange the terms to get a1 minus ib1 minus a2 minus ib2. a1 minus ib1 is equal to z1 bar and a2 minus ib2 is equal to z2 bar. So it becomes z1 bar minus z2 bars. So z1 minus z2 whole bar is equal to z1 bar minus z2 bar. Ninth property, z1 into z2 whole bar is equal to z1 bar into z2 bar. Suppose z1 is equal to a1 plus ib1 and z2 is equal to a2 plus ib2. So z1 bar is equal to a1 minus ib1 and z2 bar is equal to a2 minus ib2. z1 z2 whole bar is equal to a1 plus ib1 into a2 plus ib2 whole bar. We can simplify this as a1 a2 minus b1 b2 plus I into a1 b2 plus a2 b1 whole bar. Now we can take conjugate of this complex number and it will be a1 a2 minus b1 b2 minus I into a1 b2 plus a2 b1. We can rewrite this as a1 minus ib1 into a2 minus ib2. a1 minus ib1 is equal to z1 bar and a2 minus ib2 is equal to z2 bar. So this becomes z1 bar into z2 bar. So z1 z2 whole bar is equal to z1 bar into z2 bar. 10th property, z1 upon z2 whole bar is equal to z1 bar upon z2 bar. z1 upon z2 whole bar is equal to a1 plus ib1 upon a2 plus ib2 whole bar. We will multiply both numerator and denominator by conjugate of denominator. Conjugate of denominator is a2 minus ib2. So numerator and denominator both are multiplied by a2 minus ib2. So this can be simplified as a1 a2 plus b1 b2 plus I into b1 a2 minus a1 b2 upon a2 square plus b2 square whole bar. Now we will write this complex number in standard form and take the conjugate of it. So it will become a1 a2 plus b1 b2 upon a2 square plus b2 square minus I into b1 a2 minus a1 b2 upon a2 square plus b2 square. This can be rewritten as a1 minus ib1 into a2 plus ib2 upon a2 minus ib2 into a2 plus ib2. a2 plus ib2 in numerator and denominator will get cancelled. And a1 minus ib1 is equal to z1 bar and a2 minus ib2 is z2 bar. So this becomes z1 bar upon z2 bar. So z1 upon z2 whole bar is equal to z1 bar upon z2 bar. Now let us see these two questions based on properties of conjugate. First question, express the following complex number in standard form. Also find its conjugate. The given number is root 5 plus 12y plus root 5 minus 12y upon root 5 plus 12y minus root 5 minus 12y. Suppose the given number is equal to z. The standard form of a complex number is a plus ib. First step to solve this is to rationalize the denominator. In our previous classes, we have learned that to rationalize the denominator, we need to multiply both numerator and denominator by conjugate of denominator. So conjugate of denominator will be equal to root 5 plus 12y plus root 5 minus 12y. Now we need to multiply both numerator and denominator by root 5 plus 12y plus root 5 minus 12y. So numerator becomes root 5 plus 12y plus root 5 minus 12y whole square and denominator is in the form a minus b into a plus b and that is a square minus b square. So on simplification it becomes 3 upon 2i. Now we will multiply both numerator and denominator by I. So numerator becomes 3i and denominator becomes 2i square. We know that I square is equal to minus 1. So z is equal to 3i upon minus 2. We can represent it in standard form as z is equal to 0 minus 3 by 2i. Z bar is equal to 0 plus 3 by 2i. We just need to change the sign in between. Second question, if a plus ib upon c plus id is equal to x plus iy, then prove that a minus ib upon c minus id is equal to x minus iy, and a square plus b square upon c square plus d square is equal to x square plus y square. Suppose this is equation number 1. Take conjugate of both the sides. So we can write a plus ib upon c plus id whole bar is equal to x plus iy bar. We know that z1 upon z2 bar is equal to z1 bar upon z2 bar. So we can write LHS as a plus ib bar upon c plus id bar is equal to x plus iy bar. Conjugate of a plus ib is equal to a minus ib. Conjugate of c plus id is equal to c minus id. Conjugate of x plus iy is equal to x minus iy. So we have proved first part. Suppose this is equation number 2. Now multiply equation number 1 with equation number 2. So LHS will be multiplied with LHS and RHS with RHS. So it becomes a plus ib into a minus ib upon c plus id into c minus id is equal to x plus iy into x minus iy. So it will be a square minus I square b square upon c square minus I square d square is equal to x square minus I square y square. We know that I square is equal to minus 1. So it becomes a square plus b square upon c square plus d square is equal to x square plus y square, which we had to prove as second part. Let us understand modulus of a complex number. The modulus of a complex number z is equal to a plus ib is denoted by mod z, two small vertical lines on either side of z, and it is defined as mod z is equal to under root a square plus b square, and that is equal to under root real z square plus imaginary z square. This is pictorial representation of mod z. Suppose there is a point A in complex plane represented by ordered pair A, B. This is A and this is B. So complex number Z is equal to A plus IB. Distance of point A from origin will be called as mod Z. We can apply Pythagoras theorem in this right angle triangle AOB. So mod Z is equal to under root A square plus B square. Now let us see properties of modulus. First property, mod z is greater than or equal to 0, mod z is greater than or equal to mod of real z, and mod z is greater than or equal to mod of imaginary z. Suppose z is equal to a plus ib. So mod z is equal to under root a square plus b square. Mod of real z is equal to mod of a, and that is equal to under root a square. Mod of imaginary z is equal to mod of b, and that is equal to under root b square. We know that a and b both are real, so their square will be positive. So a square plus b square will also be positive. So we can say that mod z is greater than or equal to 0. From here, it is clear that under root a square plus b square is greater than or equal to under root a square, and under root a square plus b square is greater than or equal to under root b square. So we can say that mod z is greater than or equal to mod of real z, and mod z is greater than or equal to mod of imaginary z. Second property, mod z is equal to mod minus z is equal to mod z bar is equal to mod minus z bar. Suppose z is equal to a plus ib. So mod z is equal to under root a square plus b square. Minus z is equal to minus a minus ib. So mod minus z is equal to under root minus a whole square plus minus b whole square, and that is equal to under root a square plus b square. Z bar is equal to a minus ib. So mod z bar is equal to under root a square plus minus b whole square, and that is equal to under root a square plus b square. Minus z bar is equal to minus a plus ib. So mod minus z bar is equal to under root minus a whole square plus b square, and that is equal to under root a square plus b square. So mod z is equal to mod minus z is equal to mod z bar is equal to mod minus z bar. Third property, z bar is equal to mod z square. Suppose z is equal to a plus ib. So z bar is equal to a minus ib. Z bar is equal to a plus ib into a minus ib. It becomes a square minus I square b square. We know that I square is equal to minus 1. So this becomes a square plus b square. We can write this as under root a square plus b square whole square. Under root a square plus b square is equal to mod z. So it becomes mod z square. Fourth property, mod z1 z2 is equal to mod z1 into mod z2. Suppose z1 is equal to a1 plus ib1 and z2 is equal to a2 plus ib2. So mod z1 is equal to under root a1 square plus b1 square and mod z2 is equal to under root a2 square plus b2 square. z1 z2 is equal to a1 plus ib1 into a2 plus ib2. This can be simplified as a1 a2 minus b1 b2 plus I into a1 b2 plus a2 b1. Now we will take mod of this complex number. So mod z1 z2 is equal to under root a1 a2 minus b1 b2 whole square plus a1 b2 plus a2 b1 whole square. So we can simplify this as under root a1 square plus b1 square into a2 square plus b2 square, or under root a1 square plus b1 square into under root a2 square plus b2 square. As we know, under root ab can be written as under root a into under root b. Under root a1 square plus b1 square is equal to mod z1, and under root a2 square plus b2 square is equal to mod z2. So this can be written as mod z1 into mod z2. So mod z1 z2 is equal to mod z1 into mod z2. Fifth property, mod z1 by z2 is equal to mod z1 upon mod z2. z2 should not be equal to 0. Suppose z1 is equal to a1 plus ib1 and z2 is equal to a2 plus ib2. So mod z1 is equal to under root a1 square plus b1 square and mod z2 is equal to under root a2 square plus b2 square. z1 by z2 is equal to a1 plus ib1 upon a2 plus ib2. Now we will rationalize the denominator by multiplying both numerator and denominator by conjugate of denominator. Conjugate of denominator will be a2 minus ib2. So numerator and denominator will be multiplied by a2 minus ib2. So this is simplified as a1 a2 plus b1 b2 upon a2 square plus b2 square plus I into b1 a2 minus a1 b2 upon a2 square plus b2 square. Now we will take mod of this complex number. So mod z1 by z2 is equal to under root a1 a2 plus b1 b2 upon a2 square plus b2 square whole square plus b1 a2 minus a1 b2 upon a2 square plus b2 square whole square. Now this can be simplified as under root a1 square plus b1 square upon a2 square plus b2 square. We can write this as under root a1 square plus b1 square upon under root a2 square plus b2 square, as under root a by b is equal to under root a upon under root b. Under root a1 square plus b1 square is equal to mod z1, and under root a2 square plus b2 square is equal to mod z2. So we can write this as mod z1 upon mod z2. So we can say that mod z1 upon z2 is equal to mod z1 upon mod z2. Sixth property, mod z1 plus z2 square is equal to mod z1 square plus mod z2 square plus twice of real z1 z2 bar. Suppose z1 is equal to a1 plus ib1 and z2 is equal to a2 plus ib2. So mod z1 is equal to under root a1 square plus b1 square and mod z2 is equal to under root a2 square plus b2 square. z1 plus z2 is equal to a1 plus a2 plus I into b1 plus b2. Now we will take mod of this complex number. So mod z1 plus z2 is equal to under root a1 plus a2 whole square plus b1 plus b2 whole square. Mod z1 plus z2 square is equal to a1 plus a2 whole square plus b1 plus b2 whole square. This can be expanded as a1 square plus a2 square plus 2a1 a2, and this can be expanded as b1 square plus b2 square plus 2b1 b2. On rearranging the terms, we will get a1 square plus b1 square plus a2 square plus b2 square plus 2a1 a2 plus 2b1 b2. a1 square plus b1 square is equal to mod z1 square, and a2 square plus b2 square is equal to mod z2 square. We will find the value of 2a1a2 plus 2b1b2. z2 bar is equal to a2 minus ib2. z1 z2 bar is equal to a1 plus ib1 into a2 minus ib2. On multiplication, we get a1 a2 plus b1 b2 plus I into b1 a2 minus a1 b2. So real of z1 z2 bar is equal to a1 a2 plus b1 b2. Twice of real z1 z2 bar is equal to 2a1 a2 plus 2b1 b2. So in place of 2a1 a2 plus 2b1 b2, we can write twice of real z1 z2 bar. So we can write mod z1 plus z2 square is equal to mod z1 square plus mod z2 square plus 2 real z1 z2 bar. Seventh property, mod z1 minus z2 square is equal to mod z1 square plus mod z2 square minus twice real of z1 z2 bar. This is very similar to property number 6. We can prove the same way. Property number 8. Mod z1 plus z2 square plus mod z1 minus z2 square is equal to twice of mod z1 square plus mod z2 square. We will get this when we add property number 6 and property number 7. Ninth property, mod of z to power n is equal to mod z to power n, where n is integer. We can prove this when we study the Myers theorem later in this chapter. Last two properties are known as triangle inequalities. We can prove them when we study complex numbers in coordinate geometry later in this chapter. Now let us see few questions based on properties of modulus. First question, if 1 plus I into 1 plus 2i into 1 plus 3i and so on up to 1 plus ni is equal to x plus iy, show that 2 into 5 into 10 and so on up to 1 plus n square is equal to x square plus y square. It is given that 1 plus I into 1 plus 2i into 1 plus 3i and so on up to 1 plus ni is equal to x plus iy. We will take modulus of both the sides. So it will be mod 1 plus I into 1 plus 2i into 1 plus 3i and so on up to 1 plus ni is equal to mod x plus iy. For left hand side, we know that mod z1 z2 is equal to mod z1 into mod z2. We can extend that for n terms. So we can write mod z1, z2, z3 and so on up to zn is equal to mod z1 into mod z2 into mod z3 and so on up to mod zn. So LHS can be written as mod 1 plus I into mod 1 plus 2i into mod 1 plus 3i and so on up to mod 1 plus ni. We will take modulus of individual complex numbers. So LHS will be under root 2 into under root 5 into under root 10 and so on up to under root 1 plus n square. Modulus of right hand side will be under root x square plus y square. Now we will square both the sides. So it will be 2 into 5 into 10 and so on up to 1 plus n square is equal to x square plus y square, which we had to prove. Second question, if alpha and beta are different complex numbers with mod beta is equal to 1, find mod beta minus alpha upon 1 minus alpha bar beta. Suppose z is equal to beta minus alpha upon 1 minus alpha bar beta. We will use this property z bar is equal to mod z square. Mod z square is equal to z bar. Our z is equal to beta minus alpha upon 1 minus alpha bar beta. This is in the form z1 upon z2 bar, and that is equal to z1 bar upon z2 bar. So this can be simplified as beta minus alpha whole bar upon 1 minus alpha bar beta whole bar. Now numerator and denominator both are in the form z1 minus z2 whole bar, and that is equal to z1 bar minus z2 bar. So this can be simplified as beta bar minus alpha bar upon 1 minus alpha beta bar. Now we will multiply numerator with numerator and denominator with denominator. So it will come out to be beta beta bar minus alpha bar beta minus alpha beta bar plus alpha alpha bar upon 1 minus alpha beta bar minus alpha bar beta plus alpha alpha bar into beta beta bar. Now beta beta bar is equal to mod beta square and alpha alpha bar is equal to mod alpha square. So we will put these values. beta beta bar is equal to mod beta square minus alpha bar beta minus alpha beta bar plus alpha alpha bar is equal to mod alpha square upon 1 minus alpha beta bar minus alpha bar beta plus alpha alpha bar is equal to mod alpha square and beta beta bar is equal to mod beta square. Now put the value mod beta is equal to 1 as it is given. So it will become 1 minus alpha bar beta minus alpha beta bar plus mod alpha square upon 1 minus alpha beta bar minus alpha bar beta plus mod alpha square. Now numerator and denominator are exactly same. So result will be equal to 1. So mod beta minus alpha upon 1 minus alpha bar beta square is equal to 1. So mod beta minus alpha upon 1 minus alpha bar beta is equal to 1. Third question, if z1 and z2 be two complex numbers such that mod 1 minus z1 bar z2 square minus mod z1 minus z2 square is equal to k into 1 minus mod z1 square into 1 minus mod z2 square. Find the value of k. Left hand side is equal to mod 1 minus z1 bar z2 square minus mod z1 minus z2 square. This is in the form mod z square. We will use this property mod z square is equal to z bar. Suppose this whole is equal to z. So mod z square is equal to z bar. Suppose this whole is equal to z. So mod z square is equal to z bar. Now this is in the form z1 minus z2 whole bar and that is equal to z1 bar minus z2 bar. So this can be simplified as 1 minus z1 z2 bar and this can be simplified as z1 bar minus z2 bar. Now we will multiply this with this and this with this to get this. Now z1 bar is equal to mod z1 square and z2 bar is equal to mod z2 square. Similarly, z1 bar is equal to mod z1 square and z2 bar is equal to mod z2 square. So we will get 1 minus mod z1 square minus mod z2 square plus mod z1 square into mod z2 square, which can be rewritten as 1 minus mod z1 square into 1 minus mod z2 square. Right hand side is given as k into 1 minus mod z1 square into 1 minus mod z2 square. When we compare left hand side with right hand side, we get k is equal to 1. Let us understand arguments of a complex number. Suppose P is a point in complex plane. It is represented by ordered pair x, y. So the complex number z is equal to x plus iy. Line OP makes an angle theta with positive real axis. This angle theta is known as one of the arguments of complex number z. It is written as theta is equal to argz. Arg is short form of argument. Argument is a multi-valued function. If theta is an argument, then 2 and pi plus theta are other arguments, where n is integer. Suppose theta is first argument, then next argument will be 2 pi plus theta. Next will be 4 pi plus theta and so on. First argument or principal argument is called as amplitude such that theta lies between minus pi to plus pi. If theta lies between minus pi to plus pi, then argument theta will be called as amplitude. Now let us understand how to calculate principal argument. Suppose z is equal to x plus iy. We have to calculate principal argument theta. So first we have to calculate alpha such that tan alpha is equal to mod y by x. Alpha is an acute angle. Then we will calculate theta. Value of theta will depend on value of alpha and position of z, whether z is in first quadrant, second quadrant, third quadrant or fourth quadrant. So we will consider 4 cases. In case 1, z is in first quadrant. This angle is alpha. We know that theta is the angle that OP makes with positive real axis. So theta is equal to alpha. In case 2, z is in second quadrant. This angle is alpha. So theta is equal to pi minus alpha. In case 3, z is in third quadrant. This is alpha. So theta is equal to minus pi minus alpha. Negative as we are measuring the angle in clockwise direction. Clockwise is supposed to be negative and anti-clockwise is supposed to be positive. Case 4. Z is in fourth quadrant. This is alpha. So theta is equal to minus alpha. Let us summarize the method to calculate theta we have just learnt. First step, calculate alpha such that tan alpha is equal to mod y by x. Here alpha is acute angle. Second step, find out position of z, whether it is in first, second, third or fourth quadrant. If z is in first quadrant, theta is equal to alpha. If z is in second quadrant, theta is equal to pi minus alpha. If z is in third quadrant, theta is equal to minus in bracket pi minus alpha or alpha minus pi. If z is in fourth quadrant, theta is equal to minus alpha. Let us see one question based on calculation of principal argument. Find the modulus and argument of each of the following complex numbers. Part A. Suppose z is equal to 1 plus root 3i and that is equal to x plus iy. Mod z is equal to under root real part of a square plus imaginary part of a square. So that comes out to be equal to 2. To calculate the principal argument, first step is to calculate alpha such that tan alpha is equal to mod imaginary z upon real z and that is equal to mod root 3 upon 1. So that is equal to root 3. Tan alpha is equal to root 3. So alpha is equal to 60 degrees or pi by 3. Here real part and imaginary part both are positive. So z is in first quadrant. So theta is equal to alpha. Alpha we have calculated as pi by 3. So theta is equal to pi by 3. Part B. Suppose z is equal to minus 2 plus 2 root 3i and that is equal to x plus iy. Mod z is equal to under root real part of a square plus imaginary part of a square. So mod z is equal to 4. To calculate principal argument, again we will calculate alpha first such that tan alpha is equal to mod imaginary z upon real z. So that is equal to mod 2 root 3 upon minus 2. Mod is always positive. So that is equal to root 3. Tan alpha is equal to root 3. So alpha is equal to pi by 3. Here real part is negative and imaginary part is positive. So z is in second quadrant. So theta is equal to pi minus alpha. Alpha is equal to pi by 3. So theta is equal to 2 pi by 3. Part C. Suppose z is equal to minus root 3 minus I and that is equal to x plus iy. Mod z is equal to under root real part of a square plus imaginary part of a square. So mod z is equal to 2. Tan alpha is equal to mod imaginary z upon real z. That is equal to mod minus 1 upon minus root 3. Mod is always positive. So that is equal to 1 upon root 3. Tan alpha is equal to 1 by root 3. So alpha is equal to 30 degrees or pi by 6. Here real part is negative and imaginary part is also negative. So z is in third quadrant. So theta is equal to minus pi minus alpha. Alpha is pi by 6. So theta is equal to minus 5 pi by 6. Part D. Suppose z is equal to 2 root 3 minus 2i. So mod z is equal to under root real part of a square plus imaginary part of a square. So mod z is equal to 4. Tan alpha is equal to mod imaginary z upon real z and that is equal to mod minus 2 upon 2 root 3. Mod is always positive, so that is equal to 1 upon root 3. Tan alpha is equal to 1 by root 3, so alpha is equal to pi by 6. Here real part is positive and imaginary part is negative, so z is in fourth quadrant. So theta is equal to minus alpha. Alpha is pi by 6, so theta is equal to minus pi by 6. Now let us see properties of arguments. First property, argument of z1, z2 is equal to argument of z1 plus argument of z2 plus 2n pi, where n is integer. If we talk only about principal arguments, we can say argument of z1, z2 is equal to argument of z1 plus argument of z2. Let us see its proof. Suppose z1 is equal to a1 plus ib1 and z2 is equal to a2 plus ib2. Argument of z1, let's say theta 1. So theta 1 is equal to tan inverse b1 upon a1. Argument of Z2, let's say theta 2. So theta 2 is equal to tan inverse B2 upon A2. Z1, Z2 is equal to A1 plus IB1 into A2 plus IB2. This can be simplified as A1 A2 minus B1 B2 plus I into A1 B2 plus A2 B1. Argument of Z1 Z2 is equal to tan inverse A1 B2 plus A2 B1 upon A1 A2 minus B1 B2. This can be rewritten as B1 upon A1 plus B2 upon A2 upon 1 minus B1 upon A1 into B2 upon A2. B1 upon A1 is equal to tan theta 1 and B2 upon A2 is equal to tan theta 2. So this can be written as tan theta 1 plus tan theta 2 upon 1 minus tan theta 1 into tan theta 2. We know this is the expansion of tan theta 1 plus theta 2. So tan inverse tan theta 1 plus theta 2 is equal to theta 1 plus theta 2. Theta 1 is the argument of Z1 and theta 2 is argument of Z2. So we can say argument of Z1 Z2 is equal to argument of Z1 plus argument of Z2. Second property, argument of Z1 by Z2 is equal to argument of Z1 minus argument of Z2 plus 2n pi, where n is integer. We can prove this property as we have proved first property. Third property, argument of Z to power n is equal to n times argument of Z plus 2k pi, where n and k are integers. We can prove this property when we study the Modulus theorem later in this chapter. Now let us see a couple of questions based on properties of arguments. First question, find argument Z if Z is equal to 3 plus 4i into 1 plus I into 1 plus root 3i upon 1 minus I into 4 minus 3i into 2i whole square. Argument of Z is equal to argument of this whole. This is in the form argument of Z to power n, which is equal to n times of argument Z. So 2 will come here. Now this is in the form argument of Z1 upon Z2, which is equal to argument of Z1 minus argument of Z2. So we can write argument of numerator minus argument of denominator. Now these two are in the form argument of Z1, Z2, Z3, which is equal to argument of Z1 plus argument of Z2 plus argument of Z3. So we can write this as 2 into argument of 3 plus 4i plus argument of 1 plus I plus argument of 1 plus root 3i minus argument of 1 minus I plus argument of 4 minus 3i plus argument of 2i plus 2k pi. Now this can be simplified as argument of Z is equal to 5 pi by 3 plus 2k pi. Here k is integer. Now we have to put the value of k such as argument of Z lies between minus pi to plus pi. So we can choose k is equal to minus 1. So argument of Z is equal to minus pi by 3. Second question, if argument of Z lies between minus pi to minus pi by 2, find argument of Z bar minus argument of minus Z bar. This angle is minus pi and this angle is minus pi by 2. It is given that argument of Z lies between minus pi to minus pi by 2. That means Z lies in third quadrant. Let's say Z is equal to minus x minus iy, so that its real and imaginary parts are negative. Z bar is equal to minus x plus iy. We just need to change the sign in between real and imaginary parts. Its real part is negative and imaginary part is positive. So Z bar lies in second quadrant. Argument of Z bar is equal to pi minus theta. Minus Z bar is equal to x minus iy. Its real part is positive and imaginary part is negative. So minus Z bar lies in fourth quadrant. So argument of minus Z bar is equal to minus theta. Now we can say argument of Z bar minus argument of minus Z bar is equal to pi minus theta minus minus theta. So it is pi. Let us understand how to represent a complex number in different forms. A complex number can be represented in 4 different forms, and they are geometrical representation, polar representation, exponential representation, and vectorial representation. We will understand them one by one. First one, geometrical representation. We have already seen this. Horizontal line is called as real axis, vertical line is called as imaginary axis. They intersect at origin. Suppose there is a point P represented by ordered pair x, y. This is x and this is y. So complex number it represents is z is equal to x plus iy. Its conjugate is x minus iy. Its modulus is under root x square plus y square. Its argument theta is equal to tan inverse y by x. This plane is called as complex plane, Argand plane or Gaussian plane. Second one, polar representation. In this figure, OQ is equal to x, also mod z cos theta, and PQ is equal to y, also mod z sin theta. So complex number z is equal to x plus iy can be written as mod z cos theta plus mod z sin theta into I. Take mod z common in both the terms. So it will be mod z into cos theta plus I sin theta. Write r in place of mod z. So z is equal to r cos theta plus I sin theta, where r is equal to mod z and theta is argument of z. This is called as polar form. If we use general value of theta, then polar form can be written as z is equal to r cos 2n pi plus theta plus I sin 2n pi plus theta, where r is equal to mod z, theta is argument of z and n is integer. Third one, exponential representation. Suppose z be a complex number such that mod z is equal to r and argument of z is equal to theta. Then z is equal to r e to power I theta is called as exponential form. Here e to power I theta is equal to cos theta plus I sin theta. This is known as Euler's formula. Also, cos theta is equal to e to power I theta plus e to power minus I theta upon 2. And sin theta is equal to e to power I theta minus e to power minus I theta upon 2i. These two are known as Euler's identities. Fourth one, vectorial representation. Suppose P is a point in complex plane that represents complex number z. So z can be represented by vector OP. Mod of vector OP is equal to mod z. Now let us see few questions based on representation of complex numbers. First question, express 1 plus 3i upon 1 minus 2i in polar and exponential form. Suppose z is equal to 1 plus 3i upon 1 minus 2i. First we will write z in standard form, that is z is equal to a plus ib. To do that, we will multiply both numerator and denominator with conjugate of denominator. Conjugate of denominator is 1 plus 2i. So we will multiply numerator and denominator with 1 plus 2i. So it comes out to be equal to minus 1 plus I. So mod z is equal to under root real part of a square plus imaginary part of a square. So mod z is equal to under root 2. To calculate argument of z, we will first calculate alpha such that tan alpha is equal to mod of imaginary z upon real z. That is equal to mod of 1 upon minus 1. Mod is always positive. So tan alpha is equal to 1 or alpha is equal to pi by 4. Here real part of z is negative and imaginary part of z is positive. So z is in second quadrant. That means theta is equal to pi minus alpha. We have calculated alpha as pi by 4. So theta is equal to 3 pi by 4. In polar form, z is equal to r cos theta plus I sin theta, where r is equal to mod z and theta is argument of z. So r is equal to under root 2 and theta is equal to 3 pi by 4. So z is equal to root 2 cos 3 pi by 4 plus I sin 3 pi by 4. In exponential form, z is equal to r e to power I theta. R is equal to root 2 and theta is equal to 3 pi by 4. So z is equal to root 2 e to power I 3 pi by 4. Second question, what is the locus of z if amplitude of z minus 2 minus 3i is pi by 4? When we are dealing with coordinate geometry, we should assume z is equal to x plus iy in place of a plus ib. So z minus 2 minus 3i is equal to x plus iy minus 2 minus 3i. It is x minus 2 plus I into y minus 3. This is in standard form. Amplitude of z minus 2 minus 3i is equal to amplitude of this. Amplitude of z minus 2 minus 3i is given as pi by 4. Amplitude of this is equal to tan inverse imaginary part upon real part, or tan inverse y minus 3 upon x minus 2. So it is tan pi by 4 is equal to y minus 3 upon x minus 2. Value of tan pi by 4 is equal to 1. So 1 is equal to y minus 3 upon x minus 2. It can be simplified as x minus y plus 1 is equal to 0. This is equation of straight line in the form ax plus by plus c is equal to 0. So locus of z is a straight line. Third question, if a complex numbers z1 and z2, argument of z1 minus argument of z2 is equal to 0, then show that mod z1 minus z2 is equal to mod of mod z1 minus mod z2. Suppose z1 is equal to r1 into cos theta 1 plus I sin theta 1, and z2 is equal to r2 into cos theta 2 plus I sin theta 2 in polar form. It is given that argument of z1 minus argument of z2 is equal to 0. So argument of z1 is equal to argument of z2. Suppose argument of z1 is equal to theta 1 and argument of z2 is equal to theta 2. So theta 1 is equal to theta 2. Let's say it is theta. Mod z1 is equal to r1 and mod z2 is equal to r2. z1 minus z2 is equal to r1 into cos theta plus I sin theta minus r2 into cos theta plus I sin theta. We can take cos theta plus I sin theta common in both the terms. So it will be r1 minus r2 into cos theta plus I sin theta. So mod z1 minus z2 is equal to under root r1 minus r2 whole square into cos square theta plus sin square theta. Value of cos square theta plus sin square theta is equal to 1. So mod z1 minus z2 is equal to under root r1 minus r2 whole square. Now we can square both the sides. So it will be mod z1 minus z2 whole square is equal to r1 minus r2 whole square. Again we can take square root of both the sides. So mod z1 minus z2 is equal to mod r1 minus r2. r1 is equal to mod z1 and r2 is equal to mod z2. So mod z1 minus z2 is equal to mod of mod z1 minus mod z2, which we had to prove. Fourth question, if xn is equal to cos pi by 2 to power n plus I sin pi by 2 to power n, prove that x1, x2, x3 and so on up to x infinity is equal to minus 1. Suppose z1 and z2 are two complex numbers. They can be written in polar form as z1 is equal to r1 into cos theta 1 plus I sin theta 1 and z2 is equal to r2 into cos theta 2 plus I sin theta 2. z1 z2 is equal to r1 r2 into cos theta 1 plus I sin theta 1 into cos theta 2 plus I sin theta 2. It can be simplified as r1 r2 into cos theta 1 cos theta 2 minus sin theta 1 sin theta 2 plus I into sin theta 1 cos theta 2 plus cos theta 1 sin theta 2. We know that this can be written as cos theta 1 plus theta 2 and this can be written as sin theta 1 plus theta 2. So z1 z2 is equal to r1 r2 into cos theta 1 plus theta 2 plus I sin theta 1 plus theta 2. Point to be noted here is when two complex numbers in polar form are multiplied, their magnitudes are multiplied and their arguments are added up in cos and sin functions. We can extend this result to n number of complex numbers. So we can say in this case x1, x2, x3 and so on up to xn is equal to r1, r2, r3 and so on up to rn into cos pi by 2 plus pi by 2 square plus pi by 2 cube plus and so on pi by 2 to power n plus I sin pi by 2 plus pi by 2 square plus pi by 2 cube plus and so on pi by 2 to power n. Here we are putting the values n is equal to 1, 2, 3 and so on up to n. This is GP series whose sum is given as S is equal to A into 1 minus R to power n upon 1 minus R, where A is first term, R is common ratio, n is the number of terms. First term is pi by 2, common ratio is 1 by 2 and number of terms are n. So S is equal to pi by 2 into 1 minus 1 by 2 to power n upon 1 minus 1 by 2. We will study this in sequences and series chapter. Here R1, R2, R3, Rn are all equal to 1. So x1, x2, x3 up to xn is equal to cos pi by 2 into 1 minus 1 by 2 to power n upon 1 minus 1 by 2 plus I sin pi by 2 into 1 minus 1 by 2 to power n upon 1 minus 1 by 2. This can be simplified as cos pi into 1 minus 1 by 2 to power n plus I sin pi into 1 minus 1 by 2 to power n. We have to get the value of infinity terms multiplied together. So we will take limit n tends to infinity on both the sides. So it will be x1, x2, x3 and so on up to x infinity is equal to cos pi into 1 minus 1 by 2 to power infinity will be equal to infinity. So 1 minus 1 by infinity plus I sin pi into 1 minus 1 by infinity. 1 by infinity is equal to 0. So it can be simplified as cos pi plus I sin pi. Value of cos pi is equal to minus 1 and sin pi as 0. So the result is minus 1, which we had to prove. Let us understand rotation theorem and the Myers theorem. First, rotation theorem. Suppose there are 2 points P and Q in complex plane. They represent complex numbers Z1 and Z2. Mod of Z1 is equal to R1 and mod of Z2 is equal to R2. Argument of Z1 is equal to theta 1 and argument of Z2 is equal to theta 1 plus theta 2. So we can write vector OP is equal to Z1 is equal to R1 into e to power I theta 1 in exponential form, where R1 is equal to mod Z1. And vector OQ is equal to Z2 is equal to R2 into e to power I theta 1 plus theta 2, where R2 is equal to mod Z2. So vector OQ is equal to R2 into, we can split this as e to power I theta 1 into e to power I theta 2. Vector OQ is equal to Z2. R2 is equal to mod Z2. E to power I theta 1 we will get from here. Z1 is equal to R1 into e to power I theta 1. So e to power I theta 1 is equal to Z1 upon R1 and R1 is equal to mod Z1. So e to power I theta 1 is equal to Z1 upon mod Z1. We can move this to left hand side. So it will be Z2 upon mod Z2 is equal to Z1 upon mod Z1 into e to power I theta 2. Z2 upon mod Z2 is equal to unit vector OQ. Z1 upon mod Z1 is equal to unit vector OP. So we can write unit vector OQ is equal to unit vector OP into e to power I theta 2. This is known as rotation theorem. What it means is we will get unit vector OQ by rotating unit vector OP by angle theta 2. Let us see one question based on rotation theorem. If the vertices of a square ABCD are Z1, Z2, Z3 and Z4, then find Z3 in terms of Z1 and Z2. Suppose ABCD is a square whose vertices are represented by complex numbers Z1, Z2, Z3 and Z4. So we can say that vector AB plus vector BC is equal to vector AC. Vector AB is equal to Z2 minus Z1 and vector AC is equal to Z3 minus Z1. Unit vector AB is equal to Z2 minus Z1 upon mod Z2 minus Z1. Unit vector AC is equal to Z3 minus Z1 upon mod Z3 minus Z1. Now we can apply rotation theorem and say that we will get unit vector AC by rotating unit vector AB by 45 degrees. So unit vector AC is equal to unit vector AB into e to power I pi by 4. Unit vector AC is equal to Z3 minus Z1 upon mod Z3 minus Z1. And unit vector AB is equal to Z2 minus Z1 upon mod Z2 minus Z1. We know that AC is equal to root 2 times of AB. So we can say that mod of Z3 minus Z1 is equal to root 2 times of mod Z2 minus Z1. E to power I pi by 4 can be written as cos pi by 4 plus I sin pi by 4. Value of cos pi by 4 and sin pi by 4 is equal to 1 by root 2. So Z3 is equal to Z2 plus I into Z2 minus Z1. Now let us understand the Myers theorem. Case 1. If n is integer, then cos theta plus I sin theta to power n is equal to cos n theta plus I sin n theta. And cos theta 1 plus I sin theta 1 into cos theta 2 plus I sin theta 2 into cos theta 3 plus I sin theta 3 and so on up to cos theta n plus I sin theta n is equal to cos theta 1 plus theta 2 plus theta 3 plus and so on up to theta n plus I sin theta 1 plus theta 2 plus theta 3 plus and so on up to theta n. Case 2. If p and q are integers and q is not equal to 0, then cos theta plus I sin theta to power p by q is equal to cos 2n pi plus p theta upon q plus I sin 2n pi plus p theta upon q, where n is equal to 0, 1, 2, 3 and so on up to q minus 1. Let us see proof of this. LHS is equal to cos theta plus I sin theta to power n. Cos theta plus I sin theta can be written as e to power I theta. So LHS is equal to e to power I theta to power n, and that is equal to e to power I n theta. Suppose n theta is equal to alpha. So LHS is equal to e to power I alpha, which can be expanded as cos alpha plus I sin alpha. Now put the value of alpha back to n theta. So it becomes cos n theta plus I sin n theta, which is RHS. Now let us see proof of this. Left hand side is cos theta 1 plus I sin theta 1 into cos theta 2 plus I sin theta 2 and so on up to cos theta n plus I sin theta n. Cos theta 1 plus I sin theta 1 is equal to e to power I theta 1. Cos theta 2 plus I sin theta 2 is equal to e to power I theta 2 and so on up to e to power I theta n. This can be written as e to power I theta 1 plus theta 2 plus theta 3 plus and so on up to theta n. Let us say theta 1 plus theta 2 plus theta 3 and so on up to theta n is equal to alpha. So LHS is equal to e to power I alpha, which can be expanded as cos alpha plus I sin alpha. Now let us put the value of alpha back as theta 1 plus theta 2 plus theta 3 plus and so on up to theta n. So it becomes cos theta 1 plus theta 2 plus theta 3 plus and so on up to theta n plus I sin theta 1 plus theta 2 plus theta 3 plus and so on up to theta n, which is right hand side. Let us see one question based on the Myers theorem. If cos alpha plus cos beta plus cos gamma is equal to 0 and also sin alpha plus sin beta plus sin gamma is equal to 0, then prove that cos 2 alpha plus cos 2 beta plus cos 2 gamma is equal to sin 2 alpha plus sin 2 beta plus sin 2 gamma is equal to 0. Suppose Z1 is equal to cos alpha plus I sin alpha, Z2 is equal to cos beta plus I sin beta, and Z3 is equal to cos gamma plus I sin gamma. So Z1 plus Z2 plus Z3 is equal to cos alpha plus cos beta plus cos gamma plus I into sin alpha plus sin beta plus sin gamma. Value of cos alpha plus cos beta plus cos gamma is equal to 0. And value of sin alpha plus sin beta plus sin gamma is equal to 0. So Z1 plus Z2 plus Z3 is equal to 0. This is equation number 1. We have to find out the value of cos 2 alpha plus cos 2 beta plus cos 2 gamma and sin 2 alpha plus sin 2 beta plus sin 2 gamma. So we will write cos alpha plus I sin alpha to power 2. As per the Myers theorem, it is equal to cos 2 alpha plus I sin 2 alpha. Cos alpha plus I sin alpha is equal to Z1. So the equation is Z1 square is equal to cos 2 alpha plus I sin 2 alpha. This is equation number 2. Similarly, Z2 square is equal to cos 2 beta plus I sin 2 beta. This is equation number 3. And Z3 square is equal to cos 2 gamma plus I sin 2 gamma. This is equation number 4. Now z1 square plus z2 square plus z3 square is equal to cos 2 alpha plus cos 2 beta plus cos 2 gamma plus I into sin 2 alpha plus sin 2 beta plus sin 2 gamma. This is equation number 5. z1 square plus z2 square plus z3 square is equal to z1 plus z2 plus z3 whole square minus 2 into z1 z2 plus z2 z3 plus z3 z1. Value of z1 plus z2 plus z3 is equal to 0 from equation number 1. So z1 square plus z2 square plus z3 square is equal to minus 2 into z1 z2 plus z2 z3 plus z3 z1. This is equation number 6. We will find out the value of this. 1 by z1 is equal to z1 to power minus 1. So it is equal to cos alpha plus I sin alpha to power minus 1. As per the Maver's theorem, it is equal to cos minus alpha plus I sin minus alpha. Cos minus alpha is equal to cos alpha and sin minus alpha is equal to minus sin alpha. So 1 by z1 is equal to cos alpha minus I sin alpha. 1 by z2 is equal to cos beta minus I sin beta. And 1 by z3 is equal to cos gamma minus I sin gamma. 1 by z1 plus 1 by z2 plus 1 by z3 is equal to cos alpha plus cos beta plus cos gamma minus I into sin alpha plus sin beta plus sin gamma. Value of cos alpha plus cos beta plus cos gamma is equal to 0 and sin alpha plus sin beta plus sin gamma is also equal to 0. So right hand side is equal to 0 and left hand side will be z2 z3 plus z1 z3 plus z1 z2 upon z1 z2 z3. So z2 z3 plus z1 z3 plus z1 z2 is equal to 0. We will put this value here. So z1 square plus z2 square plus z3 square is equal to 0. So from equation number 5, 0 is equal to cos 2 alpha plus cos 2 beta plus cos 2 gamma plus I into sin 2 alpha plus sin 2 beta plus sin 2 gamma. A complex number will be 0 when its real part as well as imaginary part is 0. So we can say that cos 2 alpha plus cos 2 beta plus cos 2 gamma is equal to 0 and sin 2 alpha plus sin 2 beta plus sin 2 gamma is also equal to 0, which we had to prove. Now let us understand n roots of unity. This is a complex plane. Draw a circle with center at origin and radius as 1 unit. Mark this point as A, where this circle intersects the real axis. Now divide this circle into n equal parts. Each of these angles is equal to 2 pi by n. Mark these points as B, C, D, E, F and so on. All these points represent some complex number and these complex numbers are called as n roots of unity. Suppose point A represents complex number z1, B represents z2, C represents z3 and so on up to z represents zn. We will find out all these complex numbers from z1 to zn or n roots of unity. Mod of all these complex numbers is equal to 1 as the radius of this circle is 1 unit. In this figure, we can say that we will get unit vector OB by rotating unit vector OA by angle 2 pi by n by applying rotation theorem. So we can say unit vector OB is equal to unit vector OA into e to power I 2 pi by n. Unit vector OB is equal to vector OB upon mod OB and unit vector OA is equal to vector OA upon mod OA. Vector OB represents Z2 and vector OA represents Z1. Mod of OB is equal to mod of OA is equal to 1. So Z2 is equal to Z1 into e to power I 2 pi by n. Similarly, we can say that we will get unit vector OC by rotating unit vector OA by angle 2 pi by n plus 2 pi by n, that is 4 pi by n. So we can say that Z3 is equal to Z1 into e to power I 4 pi by n. Let us say n roots of unity are 1, alpha 1, alpha 2 and so on up to alpha n minus 1. So z1 is equal to 1 and that is first root which is purely real. z2 is equal to alpha 1, z3 is equal to alpha 2 and so on up to zn is equal to alpha n minus 1. So z1 is equal to z1, z2 is equal to z1 into e to power I 2 pi by n, z3 is equal to z1 into e to power I 4 pi by n and so on up to zn is equal to z1 e to power I n minus 1 into 2 pi by n. We can conclude 4 points from this analysis. Point number 1. Complex numbers z1, z2, z3 and so on up to zn are n roots of unity. Point number 2. Roots are in GP with common ratio equal to e to power I 2 pi by n. Clearly z1, z2, z3 are in GP. We can find common ratio by doing z2 by z1 or z3 by z2. Let us do z3 by z2. So it will be z1 into e to power I 4 pi by n upon z1 into e to power I 2 pi by n. So we will get common ratio R is equal to e to power I 2 pi by n. Point number 3. Arguments are in AP with common difference equal to 2 pi by n. Argument of z1 is equal to 0. Argument of z2 is equal to 2 pi by n. Argument of z3 is equal to 4 pi by n. So the common difference is 2 pi by n minus 0 or 4 pi by n minus 2 pi by n and that is equal to 2 pi by n. Point number 4. z1, z2, z3 and so on up to zn are located at the vertices of a regular polygon of n sides inscribed in a unit circle having center at origin. Suppose you connect points A to B, B to C, C to D, D to E and so on. So it will form a regular polygon which is inscribed in a unit circle with center at origin and radius as 1 unit. Now let us see cube roots of unity. It is a specific case of n roots of unity with n is equal to 3. This is a complex plane. Draw a circle with center at origin and radius of 1 unit. Mark this point as A, where this circle intersects the real axis. Now divide this circle into 3 equal parts. Mark these points as B and C. They represent complex numbers z1, z2 and z3. These complex numbers are called as cube roots of unity. We will figure them out. Mod of z1, z2 and z3 is equal to 1 as the radius of this circle is 1 unit. We can write z1 is equal to 1 plus 0i which is purely real as z1 lies on real axis. z2 is equal to z1 into e to power I 2 pi by 3. We get vector OB by rotating vector OA by angle 2 pi by 3 anti-clockwise. Anti-clockwise is supposed to be positive. z1 is equal to 1 and e to power I theta can be expanded as cos theta plus I sin theta. So z2 is equal to minus 1 plus root 3 I by 2. This is called omega. z3 is equal to z1 into e to power minus I 2 pi by 3. We get vector OC by rotating vector OA by angle 2 pi by 3 clockwise. Clockwise is supposed to be negative. z1 is equal to 1 and e to power minus I theta is equal to cos theta minus I sin theta. So z3 is equal to minus 1 minus root 3I by 2. This is called omega square. If we add z1, z2 and z3, we get 0. Or we can say 1 plus omega square is equal to 0. These 4 identities you can use to solve the questions. You can verify on your own by starting from right hand side and using 1 plus omega square is equal to 0. First identity is a cube plus b cube is equal to a plus b into a plus omega b into a plus omega square b. Second identity is a cube minus b cube is equal to a minus b into a minus omega b into a minus omega square b. Third identity is a cube plus b cube plus c cube minus 3abc is equal to a plus b plus c into a plus omega b plus omega square c into a plus omega square b plus omega c. Fourth identity is x square plus x plus 1 is equal to x minus omega into x minus omega square. Now let us see a couple of questions based on n roots of unity. First question, if x square plus x plus 1 is equal to 0, then find the value of x plus 1 by x to the power 4 plus x square plus 1 by x square to the power 4 plus x cube plus 1 by x cube to the power 4 plus and so on up to x to power 97 plus 1 by x to power 97 to the power 4. We will use this identity x square plus x plus 1 is equal to x minus omega into x minus omega square. It is given that x square plus x plus 1 is equal to 0. That means x minus omega into x minus omega square is equal to 0. So x is equal to omega or omega square. Let us take x is equal to omega. Next, we will find out the value of these terms and see if there is some repeating pattern in the series. X plus 1 by x is equal to omega plus 1 by omega, and that is equal to omega square plus 1 upon omega. We will use these two identities, 1 plus omega square is equal to 0 and omega cube is equal to 1. So omega square plus 1 is equal to minus omega. So it is minus omega upon omega, and that is equal to minus 1. So the value of x plus 1 by x is equal to minus 1. X square plus 1 by x square can be written as x plus 1 by x whole square minus 2. Value of x plus 1 by x is equal to minus 1. So value of x square plus 1 by x square is equal to minus 1. X cube plus 1 by x cube can be written as x square plus 1 by x square into x plus 1 by x minus x plus 1 by x. Value of x square plus 1 by x square is equal to minus 1. And value of x plus 1 by x is equal to minus 1. So value of x cube plus 1 by x cube is equal to 2. Similarly, value of x to power 4 plus 1 by x to power 4 is equal to minus 1. Value of x to power 5 plus 1 by x to power 5 is equal to minus 1. Value of x to power 6 plus 1 by x to power 6 is equal to 2. And value of x to power 7 plus 1 by x to power 7 is equal to minus 1. We see a repeating pattern here. Minus 1, 2, minus 1, 2, then again minus 1, 2. So value is repeating after every 3 terms. Value of first 3 terms will be equal to minus 1 to power 4 plus minus 1 to power 4 plus 2 to power 4. There are total 97 terms. So we will divide 97 by 3. We get 32 as quotient and 1 as remainder. So we will multiply this value by 32 and the value of last term will be equal to that of first term, and that is equal to minus 1 to power 4. So the value of this expression comes out to be equal to 577. Second question, if 1, x1, x2 and x3 are roots of x to power 4 minus 1 is equal to 0, omega is a complex root of unity, find the value of omega minus x1 into omega minus x2 into omega minus x3 upon omega square minus x1 into omega square minus x2 into omega square minus x3. It is given that x to power 4 minus 1 is equal to 0. That means x is equal to 1 to power 1 by 4. So we have to consider 4 roots of unity. Let us say these roots are z1, z2, z3 and z4. These are shown by points A, B, C and D in complex plane. Also, they are given as 1, x1, x2 and x3. We will find out the value of these complex numbers. z1 is equal to 1 and that is equal to 1 plus 0i. It is purely real as it is on real axis. z2 is equal to z1 into e to power I pi by 2, as we get vector OB by rotating vector OA anti-clockwise by 90 degrees. And z2 is equal to x1. z3 is equal to x2 is equal to z1 into e to power I pi, as we get vector OC by rotating vector OA anti-clockwise by 180 degrees. z4 is equal to x3 is equal to z1 into e to power minus I pi by 2, as we get vector OD by rotating vector OA clockwise by 90 degrees. Clockwise is supposed to be negative. So we get the values of x1, x2 and x3. These values we will put in this expression and find out the value of expression as 1. We will use 1 plus omega square is equal to 0 and omega cube is equal to 1. Complex numbers in coordinate geometry is the most important topic in this chapter. Before we start this topic, I want to cover a couple of points in cube roots of unity which I forgot to mention in my previous video. We have seen that cube roots of unity are 1, omega and omega square, where omega is equal to minus 1 plus root 3i by 2 and omega square is equal to minus 1 minus root 3i by 2. If we do square of minus 1 plus root 3i by 2, we will get minus 1 minus root 3i by 2. That is why this is omega square. Point number 1. When 3 roots are added, that means 1 plus omega square, we will get 0. Point number 2. When 3 roots are multiplied, that is 1 into omega square, that is omega cube. So we will get 1. We need to keep in mind these two identities. 1 plus omega square is equal to 0 and omega cube is equal to 1. They will help us solve many questions. Point number 3. Complex roots are in conjugate pairs. In this case, there are 3 roots. One is purely real. Omega and omega square are conjugate of each other, as it is clear from here. Let us start complex algebra. We know that complex plane and Cartesian plane are very similar. The only difference is in Cartesian plane, we used to represent equation of a straight line, distance between 2 points, equation of circle, etc. in x, y and constant. In complex plane, we represent all those things in terms of points and constants. Points such as z1, z2, z3, etc. and constants. Constants may be real or imaginary. So we need to study all those things we have studied in coordinate geometry with respect to complex plane. Let us say distance between 2 points. Suppose A and B are 2 points. They are represented by complex numbers z1 and z2. So vector AB is equal to z2 minus z1. Distance between these points is given by mod of vector AB, and that is equal to mod of z2 minus z1. Let us understand condition of parallel lines. Suppose there are 4 points A, B, C and D. They are represented by complex numbers z1, z2, z3 and z4. So we have to find out the condition that CD is parallel to AB. We will consider 2 cases. In case 1, vector CD is in same direction of vector AB, and in case 2, vector CD is in opposite direction of vector AB. In case 1, we will get unit vector CD by rotating unit vector AB by 0 degrees or not at all rotating. In case 2, we will get unit vector CD by rotating unit vector AB by 180 degrees. So in case 1, we can write unit vector CD is equal to unit vector AB into e to power I0. Unit vector CD is equal to Z4 minus Z3 upon mod Z4 minus Z3. And unit vector AB is equal to Z2 minus Z1 upon mod Z2 minus Z1. E to power 0 is equal to 1. So we get Z4 minus Z3 upon Z2 minus Z1 is equal to mod Z4 minus Z3 upon mod Z2 minus Z1. Mod is always positive and real. So mod of this upon mod of this will be real, or right hand side will be real. So the condition is Z4 minus Z3 upon Z2 minus Z1 is purely real. In case 2, we can write unit vector CD is equal to unit vector AB into e to power I pi. E to power I pi is equal to cos pi plus I sin pi. value of cos pi is equal to -1 and value of sin pi is equal to 0. So we get z4 minus z3 upon z2 minus z1 is equal to minus mod z4 minus z3 upon mod z2 minus z1. So again, right hand side is real. So we get this condition z4 minus z3 upon z2 minus z1 is purely real. So in both the cases, we get the same condition. Now let us understand condition of perpendicular lines. Suppose there are 4 points A, B, C and D. They are represented by complex numbers z1, z2, z3 and z4. We have to find the condition that AB is perpendicular to CD. Again, we will consider two cases. In case 1, we will get unit vector CD by rotating unit vector AB by 90 degrees anti-clockwise. And in case 2, we will get unit vector CD by rotating unit vector AB by 90 degrees clockwise. So we can write in case 1, unit vector CD is equal to unit vector AB into e to power I pi by 2. Unit vector CD is equal to z4 minus z3 upon mod z4 minus z3. And unit vector AB is equal to z2 minus z1 upon mod z2 minus z1. E to power I pi by 2 can be written as cos pi by 2 plus I sin pi by 2. Value of cos pi by 2 is equal to 0 and value of sin pi by 2 is equal to 1. So we get z4 minus z3 upon z2 minus z1 is equal to mod z4 minus z3 upon mod z2 minus z1 into I. This part is purely real into I and that is purely imaginary. So we get this condition z4 minus z3 upon z2 minus z1 is purely imaginary. In case 2, we can write unit vector CD is equal to unit vector AB into e to power minus I pi by 2. E to power minus I pi by 2 can be written as cos minus pi by 2 plus I sin minus pi by 2. Cos minus theta is equal to cos theta and sin minus theta is equal to minus sin theta. Value of cos pi by 2 is equal to 0 and value of sin pi by 2 is equal to 1. So this part becomes 0 minus I. So we get z4 minus z3 upon z2 minus z1 is equal to minus mod z4 minus z3 upon mod z2 minus z1 into I. Again, right hand side is purely imaginary. So we get the condition z4 minus z3 upon z2 minus z1 is purely imaginary, which is same condition as we got in case 1. Let us understand section formula. First, internal division. Suppose AB is line segment. Point A is represented by complex number z1 and point B is represented by complex number z2. P is a point on line segment AB in such a way that AP upon PB is equal to M upon N. So we have to find out complex number Z corresponding to point P. It is given by Z is equal to mz2 plus nz1 upon M plus N. Let us see its proof. From this figure, we can say that we will get unit vector PA by rotating unit vector PB by 180 degrees anti-clockwise. So we can write unit vector PA is equal to unit vector PB into e to power I pi. Unit vector PA is equal to z1 minus z upon mod z1 minus z. And unit vector PB is equal to z2 minus z upon mod z2 minus z. E to power I pi is equal to cos pi plus I sin pi. Mod z1 minus z is equal to, let's say, mk. K is a common multiplier. So mod z2 minus z is equal to nk. So we get z1 minus z upon mk is equal to z2 minus z upon nk into minus 1. So we get z is equal to mz2 plus nz1 upon m plus n. To get z for external division, we just need to change the sign in between terms in both numerator and denominator, as we used to do in coordinate geometry. So z for external division is equal to mz2 minus nz1 upon m minus n. Let us find out midpoint of line segment joining 2 points z1 and z2. It is given by z is equal to z1 plus z2 upon 2. Let us see its proof. From section formula for internal division, we know that z is equal to mz2 plus nz1 upon m plus n. Divide both numerator and denominator by n. So we get m by n z2 plus z1 upon m by n plus 1. Here mk is equal to nk. That means m by n is equal to 1. So we will put m by n is equal to 1. So we get z is equal to z1 plus z2 upon 2. Let us find out area of a triangle whose vertices are z1, z2 and z3. It is given by delta is equal to I by 4 inside determinant z1, z1 bar 1, z2, z2 bar 1 and z3, z3 bar 1. We know that in coordinate geometry, area of a triangle whose vertices are x1, y1, x2, y2 and x3, y3 is given by delta is equal to 1 by 2 inside determinant x1, y1, 1, x2, y2, 1 and x3, y3, 1. We will start from here and reach here. So delta is equal to I by 4 inside determinant z1, z1 bar 1, z2, z2 bar 1 and z3, z3 bar 1. Suppose z1 is equal to x1 plus I by 1, z2 is equal to x2 plus I by 2 and z3 is equal to x3 plus I by 3. So z1 bar is equal to x1 minus I by 1, z2 bar is equal to x2 minus I by 2 and z3 bar is equal to x3 minus I by 3. We will add these two columns. So we can say I by 4 inside determinant 2x1, 2x2, 2x3. x1 minus I by 1, x2 minus I by 2, x3 minus I by 3. 1, 1, 1. We can take 2 out. So it will be 2I by 4 inside determinant x1, x2, x3, x1 minus I by 1, x2 minus I by 2, x3 minus I by 3, 1, 1, 1. We can split this determinant into two determinants as I by 2 inside determinant x1, x2, x3, x1, x2, x3, 1, 1, 1 plus I by 2, x1, x2, x3 minus I by 1 minus I by 2 minus I by 3, 1, 1, 1. Value of this determinant is 0 as two columns are same. Here we can take minus I out. So it will be I by 2 into minus I. Inside determinant x1, x2, x3, y1, y2, y3, 1, 1, 1. Value of minus I square is equal to 1. So delta is equal to 1 by 2 inside determinant x1, x2, x3, y1, y2, y3, 1, 1, 1, which is same as this. Let us find out condition of collinearity of 3 points z1, z2 and z3. 3 points z1, z2 and z3 will be collinear if the area of the triangle formed by them is equal to 0. Or in other words, we can say that they cannot form a triangle. From here, delta is equal to 0. It means either I is equal to 0 or determinant is equal to 0. Since I is not equal to 0, so determinant is equal to 0 is the condition. So we can say that inside determinant z1, z1 bar 1, z2, z2 bar 1 and z3, z3 bar 1 is equal to 0 is the condition of collinearity of 3 points z1, z2 and z3. Now let us talk about straight lines. We will see equation of straight lines in various forms. First one is determinant form. It is given by in determinant z, z bar 1, z1, z1 bar 1 and z2, z2 bar 1 is equal to 0. You can clearly see from where it is coming. We have just now seen that 3 points z1, z2 and z3 are collinear if in determinant z1, z1 bar 1, z2, z2 bar 1 and z3, z3 bar 1 is equal to 0. In place of z1, z2 and z3, we will take z, z1 and z2, where z is a general point, z1 and z2 are given points. So we will say that locus of a point z is a straight line if it is collinear with two given points z1 and z2. Second one is general form. It is given by az bar plus a bar z plus b is equal to 0, where a is complex and b is purely real. It is derived from determinant form. Let us see how. Determinant can be expanded as z into, we need to hide rho and column involving z and say that z1 bar into 1 minus z2 bar into 1. This is first term. Minus z bar. We need to hide row and column involving z bar and say that z1 into 1 minus z2 into 1. This is second term. Plus 1. We need to hide row and column involving 1 and say that z1 into z2 bar minus z2 into z1 bar. This is third term. That is equal to 0. So it becomes z into z1 bar minus z2 bar minus z bar into z1 minus z2 plus z1 z2 bar minus z2 z1 bar is equal to 0. This part is purely imaginary. Let us see how. Suppose z1 is equal to x1 plus iy1 and z2 is equal to x2 plus iy2. Then z1 bar is equal to x1 minus iy1 and z2 bar is equal to x2 minus iy2. Now we will do z1 z2 bar minus z2 z1 bar. So we get 2i into x2 y1 minus x1 y2, which is purely imaginary. To make this part purely real, we need to multiply both sides by I. So we will get I z into z1 bar minus z2 bar minus I z bar into z1 minus z2 plus I into z1 z2 bar minus z2 z1 bar is equal to 0. Now this part has become purely real. Take minus sign inside the bracket. So second term will be plus iz bar into z2 minus z1. Now assume I into z2 minus z1 is equal to a. So a bar is equal to I into z2 minus z1 whole bar. This is in the form z1 into z2 whole bar and that is equal to z1 bar into z2 bar. So we can write I bar into z2 minus z1 whole bar. I bar is equal to minus I and z2 minus z1 whole bar is equal to z2 bar minus z1 bar. So a bar is equal to minus I into z2 bar minus z1 bar. Take negative sign inside the bracket. So a bar is equal to I into z1 bar minus z2 bar. Now in this equation, in first term, in place of I into z1 bar minus z2 bar, we will write a bar. And in second term, in place of I into z2 minus z1, we will write a. So equation changes to a bar z plus az bar. In place of third term, we will write b. So equation will be a bar z plus az bar plus b is equal to 0, where a is a complex number and b is purely real. Third one is two-point form or parametric form. Suppose two given points are a and b. They are represented by z1 and z2. Extend line segment AB so that C lies on it. C is represented by general point Z. So we can write vector AC is equal to K times of vector AB. Vector AC is equal to Z minus Z1 and vector AB is equal to Z2 minus Z1. So Z is equal to Z1 plus K times Z2 minus Z1. This is two-point form or parametric form of a straight line, where Z is any general point, Z1 and Z2 are given points and K is a parameter. Now let us see distance of a point from a given line. In coordinate geometry, we have seen that distance of a point x1, y1 from a given line ax plus by plus c is equal to 0 is given by d is equal to mod of ax1 plus by1 plus c upon under root a square plus b square. Distance formula in complex plane is very similar. Suppose there is a point P which is representing complex number z1. Its distance from a given line az bar plus a bar z plus b is equal to 0 is given by d is equal to mod of az1 bar plus a bar z1 plus b upon mod a plus a bar. Mod a plus a bar is equal to mod a plus mod a bar. We know that mod of a complex number and mod of its conjugate, they are equal. So we can write mod a plus mod a, that is 2 mod a. That is mod a plus a bar is equal to 2 mod a. So we can put this value here to get d is equal to mod of a z1 bar plus a bar z1 plus b upon 2 mod a. Now let us see a couple of questions based on what we have studied so far. First question, find equation of a straight line passing through 1 plus 2i and 2 plus i. The given 2 points are 1 plus 2i and 2 plus i. Let's say z1 is equal to 1 plus 2i and z2 is equal to 2 plus i. To get the equation of a straight line, we will use its determinant form. So in determinant, z bar 1, z1 bar 1 and z2 bar 1 is equal to 0. We will put z1 is equal to 1 plus 2i and z2 is equal to 2 plus i. So we will get z into minus 1 minus I minus z bar into minus 1 plus I plus 6i is equal to 0. This part should be purely real, but it is purely imaginary. To make it purely real, we will multiply both sides of the equation with I. So we will get iz into minus 1 minus I minus iz bar into minus 1 plus I plus 6i square is equal to 0. We can take I inside the bracket, so it will be z into 1 minus I. We can take minus I inside the bracket, so it will be plus z bar into 1 plus I. 6i square is equal to minus 6. We can rearrange the terms to get it in the form 1 plus I z bar plus 1 minus I z plus minus 6 is equal to 0. Now it is in the form a z bar plus a bar z plus b is equal to 0. Here a is equal to 1 plus I and b is equal to minus 6. Second question, find perpendicular distance of point 2 minus I from the line 1 plus I into z minus 1 minus I into z bar plus I is equal to 0. This is the given line. This is not in general form, as this should be purely real, but this is purely imaginary. To make it purely real, we need to multiply both sides of the equation by I. So we will get I into 1 plus I into z minus I into 1 minus I into z bar plus I square is equal to 0, or minus 1 plus I into z plus minus 1 minus I into z bar minus 1 is equal to 0. We can rearrange the terms to get minus 1 minus I into z bar plus minus 1 plus I into z plus minus 1 is equal to 0. Now this is in general form as a z bar plus a bar z plus b is equal to 0. Here a is equal to minus 1 minus I and b is equal to minus 1. Perpendicular distance of a point from a given line is given by the formula d is equal to mod of a z1 bar plus a bar z1 plus b upon 2 mod a. Here z1 is the given point. So we will put the values a is equal to minus 1 minus I, z1 is equal to 2 minus I, z1 bar is equal to 2 plus I, b is equal to minus 1 to get d is equal to 3 upon 2 root 2. Let us continue with straight lines. Next one is slope of a line. Slope of a line az bar plus a bar z plus b is equal to 0 is given by omega is equal to minus a upon a bar. Here a is a complex number, line is in general form. Slope is represented by omega. If you want to calculate the angle made by the line with the positive real axis, then convert the slope to polar form and compare with e to power I 2 theta. Why to compare with e to power I 2 theta? Reason is here. A can be converted to polar form as r1 e to power I theta, and a bar can be converted to polar form as r2 e to power minus I theta. Here r1 is equal to r2 as mod a is equal to mod a bar. So omega is equal to minus e to power I theta upon e to power minus I theta. E to power minus I theta will go to numerator as e to power I theta. So omega is equal to minus e to power I 2 theta. We will do this question based on this. Third point, Slope of a line passing through 2 points z1 and z2 is given by omega is equal to z1 minus z2 upon z1 minus z2 whole bar. Again, slope is in same form as this. z1 minus z2 whole bar can be written as z1 bar minus z2 bar using property of conjugate. Question: find the angle made by the line 1 plus I into z plus 1 minus I into z bar plus 2 is equal to 0 with positive real axis. First, we will make sure that the given line is in general form. Compare the given line with the general form of a straight line. So we get A is equal to 1 minus I, A bar is equal to 1 plus I, and B is equal to 2. B should be purely real, which is correct. If A is equal to 1 minus I, A bar should be 1 plus I, which is also correct. So the line is in general form. Next, we will calculate slope of the line omega. Omega is equal to minus A upon A bar. A is equal to 1 minus I and A bar is equal to 1 plus I. So omega is equal to minus 1 minus I upon 1 plus I. Now we will multiply both numerator and denominator with conjugate of denominator. So omega comes out to be equal to I. We will convert I to polar form as 1 into e to power I pi by 2. Now we will compare omega with 1 into e to power I 2 theta. So 2 theta is equal to pi by 2 or theta is equal to pi by 4. That means this line makes an angle pi by 4 with positive real axis. Now let us talk about parallel and perpendicular lines. If two lines are parallel, their slopes omega 1 and omega 2 will be equal, as we have seen in coordinate geometry. So omega 1 is equal to omega 2. If two lines are perpendicular to each other, sum of their slopes is equal to 0. That is omega 1 plus omega 2 is equal to 0 or omega 1 is equal to minus omega 2. You need to keep in mind these two conditions in case of parallel lines and in case of perpendicular lines. If a line is given as az bar plus a bar z plus b is equal to 0, its parallel line will be az bar plus a bar z plus lambda is equal to 0. We can calculate the value of lambda by the information given in the question. If a line is given as az bar plus a bar z plus b is equal to 0, its perpendicular line will be az bar minus a bar z plus I lambda is equal to 0. We can calculate the value of lambda by the information given in the question. Just take a note how the equation of parallel line and perpendicular line is written. Next, we will solve a couple of questions based on point number 3 and point number 4. These two questions are exactly same except the words parallel and perpendicular. We will see them one by one. First question, find the equation of a line parallel to 2 plus I into z bar plus 2 minus I into z plus 4 is equal to 0 and passing through 1 minus 2i. First step is to make sure that the given line is in general form. Compare it with az bar plus a bar z plus b is equal to 0. We get b is equal to 4, a is equal to 2 plus I and a bar is equal to 2 minus I. So this part should be purely real, which is correct. If a is equal to 2 plus I, its conjugate should be 2 minus I, which is also correct. So the given line is in general form. Next, we will write its parallel line. So it is given by 2 plus I into z bar plus 2 minus I into z plus lambda is equal to 0. There will not be any change in first two terms and third term will be plus lambda. Now we will pass this line through the given point 1 minus 2i. So it should satisfy this equation. That means z is equal to 1 minus 2i. So z bar is equal to 1 plus 2i. We will put these values in this equation to get lambda is equal to 0. So the equation of required line will be 2 plus I into z bar plus 2 minus I into z is equal to 0. Second question, find the equation of a line perpendicular to 2 plus I into z bar plus 2 minus I into z plus 4 is equal to 0 and passing through 1 minus 2i. From the previous question, we know that the line is in general form. Next, we will write equation of its perpendicular line, and that is given by 2 plus I into z bar minus 2 minus I into z plus I lambda is equal to 0. We will pass this line through the given point 1 minus 2i. That means 1 minus 2i will satisfy the equation of this line, or z is equal to 1 minus 2i. So z bar is equal to 1 plus 2i. We will put these values in this equation to get the value of lambda is equal to minus 10. So the equation of required line will be 2 plus I into z bar minus 2 minus I into z minus 10i is equal to 0. This part should be purely real, but it is purely imaginary. To make it purely real, we will multiply both sides of the equation with I to get the line as minus 1 plus 2i into z bar plus minus 1 minus 2i into z plus 10 is equal to 0. Now let us see equation of perpendicular bisector of a line segment joining two given points z1 and z2. Suppose AB is line segment. Its endpoints A and B are represented by two given points z1 and z2. PQ is perpendicular bisector of AB. Take a point P on PQ. It is representing general point Z. Locus of P will remain equidistant from both the given points A and B. So we can say that mod of PA is equal to mod of PB, or mod Z minus Z1 is equal to mod Z minus Z2. This is the equation of perpendicular bisector PQ of line segment AB. Now let us see complex numbers in an equilateral triangle. If Z1, Z2 and Z3 are the vertices of an equilateral triangle and Z0 is its circumcenter, then Z1 square plus Z2 square plus Z3 square minus Z1 Z2 minus Z2 Z3 minus Z3 Z1 is equal to 0, and Z1 square plus Z2 square plus Z3 square is equal to 3Z0 square. We will see their proof. First one, Z1 square plus Z2 square plus Z3 square minus Z1 Z2 minus Z2 Z3 minus Z3 Z1 is equal to 0. Suppose ABC is an equilateral triangle. Its vertices are represented by complex numbers Z1, Z2 and Z3. We can represent its sides by vectors, vector BC, vector CA and vector AB. Angle between vectors, vector BC and vector CA is equal to 120 degrees. In physics, we have studied that to get the angle between two vectors, vectors should be connected either head to head or tail to tail. If that is not the case, we should extend one vector. Here vector BC and vector CA are connected head to tail. So we need to extend one vector. Let us extend vector BC. Now they are connected tail to tail, and the angle between them is 180 degrees minus 60 degrees. So that is 120 degrees. Now we can say we will get unit vector CA by rotating unit vector BC by 120 degrees anti-clockwise. We can write unit vector CA is equal to unit vector BC into e to power I 2 pi by 3. Unit vector CA is equal to Z1 minus Z3 upon mod Z1 minus Z3. And unit vector BC is equal to Z3 minus Z2 upon mod Z3 minus Z2. Mod Z1 minus Z3 is equal to mod Z3 minus Z2 because they are sides of an equilateral triangle which are equal. So Z1 minus Z3 is equal to Z3 minus Z2 into e to power I 2 pi by 3. Similarly, we can extend side CA and say that Z2 minus Z1 is equal to Z1 minus Z3 into e to power I 2 pi by 3. Divide equation 1 by equation 2. So we will get Z1 minus Z3 upon Z2 minus Z1 is equal to Z3 minus Z2 upon Z1 minus Z3. On simplification, we will get Z1 square plus Z2 square plus Z3 square minus Z1 Z2 minus Z2 Z3 minus Z3 Z1 is equal to 0. Second one, we have to prove that z1 square plus z2 square plus z3 square is equal to 3z0 square, where z0 is circumcenter of this equilateral triangle. Circumcenter is the point of intersection of perpendicular bisectors of the sides. They pass through opposite vertices in case of equilateral triangle. Let us say perpendicular bisectors meet the sides at P, Q and R. P is the midpoint of BC. It is represented by Z2 plus Z3 upon 2. AP is divided by O in the ratio 2 is to 1. So we can apply section formula to get Z0 and say that Z0 is equal to 2 into Z2 plus Z3 upon 2 plus 1 into Z1 upon 2 plus 1. So we will get Z0 is equal to Z1 plus Z2 plus Z3 upon 3, or Z1 plus Z2 plus Z3 is equal to 3Z0. We can square both sides of the equation to get Z1 square plus Z2 square plus Z3 square plus 2 into Z1 Z2 plus Z2 Z3 plus Z3 Z1 is equal to 9Z0 square. We can substitute value of Z1 Z2 plus Z2 Z3 plus Z3 Z1 from here as Z1 square plus Z2 square plus Z3 square. So we will get Z1 square plus Z2 square plus Z3 square is equal to 3Z0 square. Now let us talk about complex numbers and circles. We will see equations of circles in various forms, and they are standard form, general form, diametric form, 4 points concyclic form and family of circles form. We will see them one by one. First one, standard form. Consider a circle with center Z0 and radius R. Z is any general point on the circumference. So we can write mod Z minus Z0 is equal to R. This is known as standard form of the circle. Second one is general form. We can derive general form from the standard form. Square both sides of it. So we get mod Z minus Z0 square is equal to R square. This is in the form mod Z square, which can be written as Z bar using mod property. So it will be Z minus Z0 into Z minus Z0 whole bar equal to R square. Z minus Z0 whole bar can be written as Z bar minus Z0 bar using conjugate property. Now we can multiply these two and get Z bar minus Z0 bar minus Z0 Z bar plus Z0 Z0 bar is equal to R square. Or we can write it as Z bar plus in bracket minus Z0 into Z bar plus in bracket minus Z0 bar Z plus Z0 Z0 bar minus R square is equal to 0. Now assume this is equal to A. So A is equal to minus Z0. So A bar is equal to minus Z0 bar. So we can write this as ZZ bar plus AZ bar plus A bar Z plus B is equal to 0, where B is equal to Z0 Z0 bar minus R square, which is purely real. This is called as general form of the circle, where A is equal to minus Z0 and B is equal to mod Z0 square minus R square. Z0 Z0 bar can be written as mod Z0 square. So general form of the circle is this, with center Z0 is equal to minus A and radius R is equal to under root mod A square minus B. Third one is diametric form. Consider a circle with a diameter AB. Its endpoints A and B are represented by complex numbers Z1 and Z2. Z is a general point on the circumference. Then argument of Z minus Z2 is equal to angle CBD. Suppose this is positive real axis. Then argument of Z minus Z2 is equal to angle CBD. And argument of Z minus Z1 is equal to this angle, angle CAB. This angle is external to triangle ABC with side AB extended. So angle CBD is equal to angle CAB plus angle ACB. And we know that this angle is 90 degrees. So we can write argument of z minus z2 is equal to argument of z minus z1 plus pi by 2. Or we can say argument of z minus z2 minus argument of z minus z1 is equal to pi by 2. Using argument property, we can write argument of z1 minus argument of z2 is equal to argument of z1 by z2. So argument of z minus z2 upon z minus z1 is equal to pi by 2. We can write minus pi by 2 as well because z can be downwards also. Now, argument of some complex number is equal to plus minus pi by 2. So, the number will be purely imaginary. It can lie on positive side of imaginary axis or on the negative side of imaginary axis. So, this complex number is purely imaginary. That is, z minus z2 upon z minus z1 is purely imaginary. Suppose a complex number is purely imaginary. So, z plus z bar is equal to 0. Let us see how. Suppose z is equal to iy, so z bar is equal to minus iy. So z plus z bar is equal to iy minus iy, that is equal to 0. So we can write that z minus z2 upon z minus z1 plus z minus z2 upon z minus z1 whole bar is equal to 0 as per this. So z minus z2 upon z minus z1 whole bar is in the form z1 upon z2 whole bar. It can be simplified as z1 bar upon z2 bar using conjugate property. Now z1 minus z2 whole bar can be written as z1 bar minus z2 bar. So it can be written as z bar minus z2 bar and denominator can be written as z bar minus z1 bar. So after simplification, we will get z minus z1 into z bar minus z2 bar plus z minus z2 into z bar minus z1 bar is equal to 0. This is called as diametric form of the circle. Fourth one is 4 points concyclic form. Suppose A, B, C, D are 4 points which are concyclic. That means they lie on the circumference of the same circle. They are represented by complex numbers z1, z2, z3 and z4. We know that angles marked by theta are equal as they are subtended by the same chord AB. Now consider triangle ABC. Angle CBE is external angle which will be equal to sum of opposite internal angles, that is angle CAB plus angle ACB. So we can write argument of z3 minus z2 is equal to argument of z3 minus z1 plus angle theta. Now change the sides. We can write argument of z3 minus z2 minus argument of z3 minus z1 is equal to theta. Argument of x minus argument of y is equal to argument of x by y using argument property. So argument of z3 minus z2 upon z3 minus z1 is equal to theta. This is equation number 1. Now consider triangle ABD. Angle DBE is external angle which will be equal to sum of opposite internal angles, that is angle DAB plus angle ADB. So we can write argument of z4 minus z2 is equal to argument of z4 minus z1 plus angle theta. Now we can change the sides and write argument of z4 minus z2 minus argument of z4 minus z1 is equal to theta. Now again, argument of x minus argument of y can be written as argument of x by y. This is equation number 2. Now we can equate equation number 1 and equation number 2 as theta is equal to this and theta is equal to this. So LHS will be equal. So we can write argument of z3 minus z2 upon z3 minus z1 is equal to argument of z4 minus z2 upon z4 minus z1. Now we can change the side to left hand side. So it will be argument of z3 minus z2 upon z3 minus z1 minus argument of z4 minus z2 upon z4 minus z1 is equal to 0. Now we want to change this sign. So we will make plus and switch numerator to denominator and denominator to numerator. So we will write plus argument of z4 minus z1 upon z4 minus z2. Now argument of x plus argument of y is equal to argument of x into y. So argument of x into y is equal to 0. Let us say this is some complex number. So if argument of any complex number is equal to 0, that means complex number is purely real. Now suppose the complex number is z. So we can write z is equal to z bar if z is purely real. Let us see how. Suppose z is purely real, so we can assume z is equal to x. So z bar is equal to x. That means z is equal to z bar. Now we will write this is equal to this bar. So z3 minus z2 upon z3 minus z1 into z4 minus z1 upon z4 minus z2 is equal to z3 minus z2 upon z3 minus z1 into z4 minus z1 upon z4 minus z2 whole bar. Whole bar can be written as z1 into z2 whole bar is equal to z1 bar into z2 bar. Now this is in the form z1 by z2 whole bar, which can be written as z1 bar upon z2 bar. Now this can be expanded as z3 bar minus z2 bar. So we can do the same to all. So we will get z3 minus z2 upon z3 minus z1 into z4 minus z1 upon z4 minus z2 is equal to z3 bar minus z2 bar upon z3 bar minus z1 bar into z4 bar minus z1 bar upon z4 bar minus z2 bar. This is called as 4 points concyclic form. Last one is family of circles form. Suppose there is a circle given by the equation s is equal to 0 and there is a straight line given by the equation L is equal to 0. Their intersection points are A and B given by complex numbers z1 and z2. Then there will be infinite circles which will pass through points A and B and they are called as family of circles. Their equation is given by s plus lambda L is equal to 0. In terms of z1 and z2, equation is given by z minus z1 into z bar minus z2 bar plus z minus z2 into z bar minus z1 bar plus lambda indeterminate z bar 1, z1 z1 bar 1, z2 z2 bar 1 is equal to 0. Now let us see how centroid, incenter, excenter, circumcenter and orthocenter are represented by a complex number when three vertices of a triangle are represented by complex numbers z1, z2 and z3. First one is centroid. Suppose ABC is a triangle. Its vertices are represented by complex numbers z1, z2 and z3. Centroid is the point of intersection of three medians. In this figure, AP, PQ and CR are three medians. Their point of intersection, that is centroid, is represented by G. Suppose this is represented by complex number Z. So Z is equal to Z1 plus Z2 plus Z3 upon 3. Let us prove that. AP is one median. That means P is the midpoint of BC. It will be represented by Z2 plus Z3 upon 2. G divides AP in 2:1 ratio. That means AG upon GP is equal to 2:1. So we can apply section formula here and say that Z is equal to 2 into Z2 plus Z3 upon 2 plus 1 into Z1 upon 2 plus 1. So Z comes out to be equal to Z1 plus Z2 plus Z3 upon 3. Next one is incenter. Suppose ABC is a triangle whose vertices are represented by complex numbers Z1, Z2 and Z3. Incenter is the point of intersection of angle bisectors. In this figure, AP, BQ and CR are angle bisectors. They intersect at point I. I is called incenter and this circle is called incircle. Suppose I is represented by complex number z. So z is equal to az1 plus bz2 plus cz3 upon a plus b plus c, where a, b and c are sides opposite to angles a, b and c respectively. Let us prove it. In triangle ABC, AP is the angle bisector of angle A. So we can apply angle bisector theorem in triangle ABC and say that AB upon AC is equal to BP upon PC, or C by B is equal to BP by PC. So BP and PC are in the ratio C is to B. Let us say BP is equal to CK and PC is equal to BK, where K is common multiplier. Also, BC is equal to BP plus PC. BC is equal to A. BP is equal to CK and PC is equal to BK. So A is equal to CK plus BK, or K is equal to A upon B plus C. Let us say point P is represented by complex number Z dash. So we can apply section formula in BC to figure out Z dash and say that Z dash is equal to BP into Z3 plus PC into Z2 upon BP plus PC, or Z dash is equal to CZ3 plus BZ2 upon B plus C. Next, we will apply angle bisector theorem in triangle ABP and say that BP upon BA is equal to PI upon IA. BP is equal to CK, BA is equal to C, PI is equal to Z minus Z dash, and IA is equal to Z1 minus Z. Value of Z dash can be put from here. So after simplification, we get Z is equal to AZ1 plus BZ2 plus CZ3 upon A plus B plus C. Next one is excenters. Suppose ABC is a triangle whose vertices are given by complex numbers Z1, Z2 and Z3. Extend the side AB and AC so that external angles are formed. Do the bisector of these external angles so that they meet at I1. So I1 is called as excenter opposite to angle A. We can make a big circle which will touch all these three sides, this side and these two extended sides. So I1 is given by minus AZ1 plus BZ2 plus CZ3 upon minus A plus B plus C. Similarly, I2 is equal to AZ1 minus BZ2 plus CZ3 upon A minus B plus C. And I3 is equal to AZ1 plus BZ2 minus CZ3 upon A plus B minus C. We can get their proof the similar way we have found incenter. Next one is circumcenter. Suppose ABC is a triangle whose vertices are represented by complex numbers Z1, Z2 and Z3. Circumcenter is the point of intersection of perpendicular bisectors of the sides. In this figure, it is shown by O. Then OA is equal to OB is equal to OC, that is radius of the circumcircle. Circumcircle touches the vertices A, B and C of the triangle. Suppose O is represented by complex number Z. Then Z is equal to Z1 sin 2A plus Z2 sin 2B plus Z3 sin 2C upon sin 2A plus sin 2B plus sin 2C. This formula is useful only if angles A, B and C are given. Otherwise, you need to follow alternate method. First step, write the equation of a straight line BC that passes through Z2 and Z3. Suppose its equation is given by A1 Z bar plus A1 bar Z plus B1 is equal to 0, where A1 is equal to I into Z3 minus Z2 and B1 is equal to I into Z2 Z3 bar minus Z2 bar Z3. Next, we will write the equation of a straight line that is perpendicular to BC, and it is given by A1 Z bar minus A1 bar Z plus I lambda 1 is equal to 0. Suppose this is equation number 1. We will pass this line through point P, which is midpoint of BC, and it is given by Z2 plus Z3 by 2. So we will get value of lambda 1. Similarly, we will write equation of a straight line AB that passes through Z1 and Z2. Suppose it is given by A2 Z bar plus A2 bar Z plus B2 is equal to 0, where A2 is equal to I into Z2 minus Z1 and B2 is equal to I into Z1 Z2 bar minus Z1 bar Z2. Next, we will find the equation of a straight line that is perpendicular to AB. And it is given by A2 Z bar minus A2 bar Z plus I lambda 2 is equal to 0. Suppose this is equation number 2. We will pass this line through point R, which is midpoint of AB, and it is given by Z1 plus Z2 by 2. We will get the value of lambda 2. Finally, we will solve equation number 1 and 2 to get Z, which will be circumcenter. Last one is orthocenter. Suppose ABC is a triangle whose vertices are represented by complex numbers Z1, Z2 and Z3. Orthocenter is the point of intersection of perpendiculars drawn on the sides from opposite vertices. In this figure, AP, BQ and CR are the perpendiculars drawn on the sides from opposite vertices. Their point of intersection is called orthocenter. Suppose O is represented by complex number Z. Then Z is equal to Z1 tan A plus Z2 tan B plus Z3 tan C upon tan A plus tan B plus tan C. This formula is useful only if angles A, B and C are also given. Otherwise, you need to follow alternate method. First step, find the equation of a straight line BC that passes through Z2 and Z3. Suppose the equation of a straight line is given by A1 Z bar plus A1 bar Z plus B1 is equal to 0, where A1 is equal to I into Z3 minus Z2 and B1 is equal to I into Z2 Z3 bar minus Z2 bar Z3. Next, we will find equation of a straight line that is perpendicular to BC. It is given by A1 Z bar minus A1 bar Z plus I lambda 1 is equal to 0. We will pass this line through Z1 to get lambda 1. Suppose this is equation number 1. Similarly, we will find the equation of a straight line AB that passes through Z1 and Z2. Suppose its equation is given by A2 Z bar plus A2 bar Z plus B2 is equal to 0, where A2 is equal to I into Z2 minus Z1 and B2 is equal to I into Z1 Z2 bar minus Z1 bar Z2. Next, we will find the equation of a straight line that is perpendicular to AB, and that is given by A2 Z bar minus A2 bar Z plus I lambda 2 is equal to 0. We will pass this line through Z3 to get lambda 2. Suppose this is equation number 2. Now we will solve equation number 1 and equation number 2 to get Z, which will be orthocenter. We have talked about complex numbers in triangles, straight lines and circles. We are yet to cover ellipse, parabola and hyperbola, which we will cover in respective conic section chapters. Let us solve previous year's JEE questions. First question, if 1 plus I upon 1 minus I to the power m by 2 is equal to 1 plus I upon 1 minus I to the power n by 3, where m and n are natural numbers, then the greatest common divisor of the least values of m and n is. This question was asked in JEE Mains 2020. First step is to rationalize the denominator on both the sides inside the bracket. On both the sides inside the bracket, it is 1 plus I upon 1 minus I. So we will multiply both numerator and denominator by conjugate of denominator, and conjugate of denominator is 1 plus I. So we can simplify it as I to power m by 2 is equal to I to power n by 3. On both the sides, base is same, so we can equate exponents and say that m by 2 is equal to n by 3. or m by n is equal to 2 by 3. Next, we have to find out greatest common divisor of the least values of m and n, where m and n are natural numbers. So we will make a table and write the values of m, n and common divisor. When m is equal to 2 and n is equal to 3, common divisor is 1. When m is equal to 4 and n is equal to 6, common divisor is 2. When m is equal to 6 and n is equal to 9, common divisor is 3. When m is equal to 8 and n is equal to 12, common divisors are 2 and 4. So far 4 is the greatest common divisor for least values of m and n. Let us look out for the next one. When m is equal to 10 and n is equal to 15, common divisor is 5. This looks like greatest common divisor, but it is not for the least values of m and n. So our answer is 4. 4 is the greatest common divisor for the least values of m and n, where m is equal to 8 and n is equal to 12. So our answer is 4. So we will fill 4 here. Second question, the sum of 162th power of the roots of the equation x cube minus 2x square plus 2x minus 1 is equal to 0 is. This question was asked in JEE Mains 2021. The given equation is x cube minus 2x square plus 2x minus 1 is equal to 0. Put x is equal to 1 to check whether 1 is one root of the equation or not. We get LHS is equal to RHS. That means 1 is one root of the equation. We can rewrite this equation as x cube minus x square plus x minus 1 is equal to 0. So that we can take x minus 1 common. In term 1 and 2, we can take x square common. So inside the bracket, it is x minus 1. In term 3 and 4, we can take minus x common. So that inside bracket, it is x minus 1. And in term 5 and 6, we can take plus 1 common. So that inside the bracket, it is x minus 1. Now we can take x minus 1 common in 3 terms. So it will be x minus 1 into x square minus x plus 1 is equal to 0. We have factorized the given equation as x minus 1 into x square minus x plus 1 is equal to 0. This means either x minus 1 is equal to 0 or x square minus x plus 1 is equal to 0. We have already seen that x is equal to 1 or 1 is one root of the given equation. Other two roots we will find from this quadratic equation. Let us say other two roots are x2 and x3. So x2 comma x3 is equal to minus b plus minus under root b square minus 4ac upon 2a. So x2 and x3 come out to be x2 is equal to 1 plus root 3i by 2 and x3 is equal to 1 minus root 3i by 2. So the three roots are 1, 1 plus root 3i by 2 and 1 minus root 3i by 2. Now we have to get the sum of 162th power of the roots. So it will be 1 to power 162 plus 1 plus root 3i by 2 to power 162 plus 1 minus root 3i by 2 to power 162. 1 to power 162 is equal to 1. Second term can be written as 1 by 2 plus root 3i by 2 to power 162. And third term can be written as 1 by 2 minus root 3i by 2 to power 162. 1 by 2 means cos pi by 3. Root 3 by 2 means sin pi by 3. Similarly, 1 by 2 means cos pi by 3 and minus root 3 by 2 means minus sin pi by 3. Now we can apply the Myers theorem in second and third term. So this power will be multiplied with the angles. So it will be 1 plus cos 162 pi by 3 plus I sin 162 pi by 3 plus cos 162 pi by 3 minus I sin 162 pi by 3. So this term and this term will get cancelled and this will be added to give 2 cos 162 pi by 3. This can be simplified as 54 pi, and 54 pi is a multiplier of 2 pi. So we can write 2 pi into 27 plus 0. So value of this is equal to cos 0, and that is 1. So value of the expression is 1 plus 2 into 1, and that is 3. So our answer is 3. Third question, let z be the complex number such that mod z minus I upon z plus 2i is equal to 1 and mod z is equal to 5 by 2. Then the value of mod z plus 3i is, these are the options given. This question was asked in JEE Mains 2020. It is given that mod z minus I upon z plus 2i is equal to 1. Using mod property, we can write mod z1 by z2 is equal to mod z1 upon mod z2. Cross multiply to get mod z minus I is equal to mod z plus 2i. Suppose this is equation number 1. Now assume z is equal to a plus ib. So z minus I is equal to a plus b minus 1 into I. Mod z minus I is equal to under root a square plus b minus 1 whole square. Z plus 2i is equal to a plus b plus 2 into I, and mod z plus 2i is equal to under root a square plus b plus 2 whole square. As per equation 1, mod z minus I is equal to mod z plus 2i. So under root a square plus b minus 1 whole square is equal to under root a square plus b plus 2 whole square. Square both the sides and simplify to get b is equal to minus 1 by 2. It is given that mod z is equal to 5 by 2. Mod z is equal to under root a square plus b square. Square both the sides to get a square plus b square is equal to 5 by 2 whole square. Put the value of b as minus 1 by 2 and simplify to get the value of a is equal to plus minus root 6. We have to calculate the value of mod z plus 3i, and mod z plus 3i is equal to under root a square plus b plus 3 whole square. Put the value of a and b from here to get mod z plus 3i is equal to 7 by 2. So the correct option is option C. Fourth question, let alpha is equal to minus 1 plus I root 3 by 2 if a is equal to 1 plus alpha into summation of alpha to power 2k where k is 0 to 100 and b is equal to summation of alpha to power 3k where k is 0 to 100, then a and b are the roots of the quadratic equation. These are the options given. This question was asked in JEE Mains 2020. By just looking at alpha, you know that this is omega. Recall the cube roots of unity. They are given by 1, omega and omega square, where omega is equal to minus 1 plus root 3i by 2 and omega square is equal to minus 1 minus root 3i by 2. So replace alpha by omega. That will give the advantage of using two identities. 1 plus omega square is equal to 0 and omega cube is equal to 1. So let us start. Given a is equal to 1 plus alpha into summation of alpha to power 2k from k is equal to 0 to 100. Replace alpha by omega and expand the series. So a is equal to 1 plus omega into omega to power 0 plus omega square plus omega to power 4 plus and so on up to omega to power 200. From k is equal to 0 to k is equal to 100, there are 101 terms, and this is GP series. Sum of n terms of a GP series is given by the formula Sn is equal to a into 1 minus r to power n upon 1 minus r, where a is first term, r is the common ratio, and n is the number of terms. First term is omega to power 0, and common ratio r is equal to omega square upon omega to power 0 or omega to power 4 upon omega square. So r is equal to omega square. Number of terms n is equal to 101. So Sn is equal to omega to power 0 into 1 minus omega square to power 101 upon 1 minus omega square. So after simplification, A is equal to 1 minus omega to power 202 upon 1 minus omega. Now we can write omega to power 202 in terms of omega cube, because we know omega cube is equal to 1. So divide 202 by 3. We get 67 as quotient and 1 as remainder. So 202 can be written as 3 into 67 plus 1. So omega to power 202 can be written as omega to power 3 to power 67 into omega. Omega cube is equal to 1. So this part is omega. Numerator is 1 minus omega and denominator is also 1 minus omega. So A is equal to 1. B is equal to summation of alpha to power 3k from k is equal to 0 to 100. So replace alpha by omega and expand the series. So B is equal to omega to power 0 plus omega cube plus omega to power 6 plus and so on up to omega to power 300. Again, there will be 101 terms from k is equal to 0 to k is equal to 100. And this is GP series. But this time we will not apply this formula. Rather, we will manipulate the terms as the terms are already in the form omega cube. First term is omega to power 0, so that is 1. Second term is omega cube, so that is 1. Third term is omega to power 6, so it can be written as omega cube whole square, and value of omega cube is equal to 1. So third term will also be 1. Fourth term is omega to power 9, so it can be written as omega cube whole cube. So it will be 1. Last term will be omega cube to power 100. Omega cube is 1. So again last term will also be 1. So there will be 101 terms and value of each term is 1. So summation will be 1 into 101. So B is equal to 101. Now we have got the value of A and B. So quadratic equation whose roots are a and b will be given by x minus a into x minus b is equal to 0. Put the value of a and b from here. So quadratic equation is x square minus 102x plus 101 is equal to 0. So the correct option is option A. Fifth question, let the lines 2 minus I into z is equal to 2 plus I into z bar and 2 plus I into z plus I minus 2 into z bar minus 4I is equal to 0. Here I square is equal to minus 1 be the normal to a circle C. If the line iz plus z bar plus 1 plus I is equal to 0 is tangent to this circle C, then its radius is. These are the options given. This question was asked in JEE Mains 2021. Suppose this is the given circle C. PO and QO are two given normals. They intersect at O, which is center of the circle. So first we will solve the given normals PO and QO to get center of the circle. Then we will calculate the perpendicular distance OR between the center of the circle and the given tangent. This perpendicular distance OR will be radius of the circle. So let us start. Suppose z is equal to x plus iy. So z bar is equal to x minus iy. We will put these values of z and z bar in n1. So we will get 2 minus I into x plus iy is equal to 2 plus I into x minus iy. This gives x is equal to 2y. Suppose this is equation number 1. Now we will put the values of z and z bar in n2. So we will get 2 plus I into x plus iy plus I minus 2 into x minus iy minus 4i is equal to 0. This gives x plus 2y minus 2 is equal to 0. Suppose this is equation number 2. Now we will solve equation number 1 and equation number 2 to get x is equal to 1 and y is equal to 1 by 2. So the center of the circle will be x plus iy, and that is 1 plus 1 by 2i. Given equation of tangent is iz plus z bar plus 1 plus I is equal to 0. Rearrange the terms to get z bar plus iz plus 1 plus I is equal to 0. Compare it with the equation of a straight line in general form, which is az bar plus a bar z plus b is equal to 0. where b is purely real, but 1 plus I is imaginary. To make this part purely real, we need to multiply both sides of the equation with 1 minus I. So we will get 1 minus I z bar plus 1 plus I z plus 2 is equal to 0. Now the equation of tangent is in general form with a is equal to 1 minus I, a bar is equal to 1 plus I and b is equal to 2. Now we are ready to calculate the perpendicular distance OR between the point Z1 and the straight line AZ bar plus A bar Z plus B is equal to 0. And OR is given by mod A Z1 bar plus A bar Z1 plus B upon 2 mod A. We can start putting the values. A is equal to 1 minus I, A bar is equal to 1 plus I, B is equal to 2, Z1 is equal to 1 plus 1 by 2I, Z1 bar is equal to 1 minus 1 by 2I and mod A is equal to under root 2. So we will get OR or radius of the circle equal to 3 upon 2 root 2. So the correct option is option D. Sixth question. Let Z be those complex numbers which satisfy mod Z plus 5 is less than or equal to 4 and Z into 1 plus I plus Z bar into 1 minus I is greater than or equal to minus 10. I is equal to under root minus 1. If the maximum value of mod Z plus 1 square is alpha plus beta root 2, then the value of alpha plus beta is. This question was asked in JEE Mains 2021. It is given that Z satisfies these two inequalities. So first let us understand its meaning. First inequality is mod Z plus 5 is less than or equal to 4. This can be written as mod Z minus in bracket minus 5 is less than or equal to 4. This matches with equation of a circle in standard form, which is given by mod Z minus Z0 is equal to R, where Z0 is the center and R is the radius. Inequality less than or equal to means Z lies somewhere on the circle or inside the circle. Let us understand the meaning of second inequality. It is given as Z into 1 plus I plus Z bar into 1 minus I is greater than or equal to minus 10. We can rearrange the terms to get 1 minus I into Z bar plus 1 plus I into Z plus 10 is greater than or equal to 0. This matches with equation of a straight line in general form, which is given by AZ bar plus A bar Z plus B is equal to 0. To get the idea how this line can be sketched in complex plane, put Z is equal to X plus IY. So Z bar is equal to X minus IY. So the inequality will be 1 minus I into X minus IY plus 1 plus I into X plus IY plus 10 is greater than or equal to 0, which can be simplified as X minus Y plus 5 is greater than or equal to 0 or Y is less than or equal to X plus 5. Consider for a moment Y is equal to X plus 5, which is very familiar equation of a straight line in the form Y is equal to mx plus c in Cartesian plane. Slope m is equal to 1 and y-intercept c is equal to 5. So this line will make 45-degree angle with positive real axis. Its y-intercept is 5 units and its slope is 1. So its x-intercept is also 5 units. So this line will pass through the center of this circle. We need to consider the intersection of this circle and straight line. So which part should we consider? This part or this part? To make sure which part we need to consider, we need to see this inequality again. So y is less than or equal to x plus 5. If you put the values of x as minus 5, minus 4, minus 3, minus 2, then you will see y is increasing. That means when x is increasing, y is also increasing. So you need to consider this part. So z will lie somewhere in this region. We need to find maximum value of mod z plus 1 square. Mod z plus 1 is equal to mod x plus iy plus 1. Mod z plus 1 square is equal to x plus 1 whole square plus y square. Mod z plus 1 square will be maximum when x and y both are maximum. So where should the point Z lie in this region so that its x and y values are maximum? It should be at point B. So first we will calculate the points of intersection of this circle and this straight line. For that, we need to consider these two curves. Mod z plus 5 is equal to 4, that is equation of circle. And the line 1 minus I z bar plus 1 plus I z plus 10 is equal to 0. We will put z is equal to x plus iy and z bar is equal to x minus iy. So equation of circle we will get is x square plus y square plus 10x plus 9 is equal to 0, and equation of a straight line as y is equal to x plus 5. We can solve equation 1 and equation 2 to get 2 points. When x is equal to minus 5 plus 2 root 2, y is equal to 2 root 2, and when x is equal to minus 5 minus 2 root 2, y is equal to minus 2 root 2. Since point B is in third quadrant, so x and y both will be negative. So we will consider second point. So value of x is equal to minus 5 minus 2 root 2 and value of y is equal to minus 2 root 2. So mod z plus 1 square is equal to, we will put value of x and y here. So mod z plus 1 square is equal to 32 plus 16 root 2. Compare this value with alpha plus beta root 2. So alpha is equal to 32 and beta is equal to 16. So alpha plus beta is equal to 32 plus 16, and that is 48. So our answer is 48. Seventh question, if the equation A mod z square plus alpha bar z plus alpha z bar whole bar plus d is equal to 0 represents a circle where A, D are real constants, then which of the following condition is correct? These are the options given. This question was asked in JEE Mains 2021. Given equation of circle is A mod z square plus alpha bar z plus alpha z bar whole bar plus d is equal to 0. Mod z square can be written as z bar. This is in the form z1 plus z2 whole bar, which is equal to z1 bar plus z2 bar using conjugate property. This is in the form z1 into z2 whole bar, which is equal to z1 bar into z2 bar. Bar of alpha bar is equal to alpha and bar of z is equal to z bar. Similarly, this is in the form z1 into z2 whole bar, which is equal to z1 bar into z2 bar. Bar of alpha is alpha bar and bar of z bar is equal to z. Now divide this whole equation by a. So we get zz bar plus alpha by a z bar plus alpha bar by a z plus d by a is equal to 0. Suppose this is equation number 1. We know the general form of the equation of circle is given by zz bar plus pz bar plus p bar z plus q is equal to 0. Here I have replaced letters A and B by P and Q to avoid the confusion of same letter A. Here center Z0 is equal to minus P and radius R is equal to under root mod minus P square minus Q. Now compare equation 1 and 2 term by term. So it will be P is equal to alpha by A, P bar is equal to alpha bar by A and Q is equal to D by A. So radius R is equal to under root mod minus alpha by A square minus D by A. First thing you will notice here is A cannot be equal to 0. And inside the bracket stuff also cannot be equal to 0. Because in that case, radius will be 0, so circle will be a point. So the inequality we will write, this part is greater than 0. Now this is mod z1 upon z2 square. So it can be written as mod z1 square upon mod z2 square. So it will be mod alpha square upon mod a square can be written as a square if a is real. Minus d by a is greater than 0. Now take a square as LCM. So it will be mod alpha square minus ad upon a square is greater than 0. If a is real, a square is always positive. So for this inequality to be greater than 0, numerator should also be greater than 0. So the condition is mod alpha square minus AD is greater than 0 and A is not equal to 0. Also A is real. So the correct option is option B. Eighth question, the least value of mod z where z is a complex number which satisfies the inequality exponent of mod z plus 3 into mod z minus 1 upon mod z plus 1 into log 2 base c is greater than or equal to log of mod 5 root 7 plus 9i to the base root 2, I is equal to under root minus 1 is equal to. These are the options given. This question was asked in JEE Mains 2021. First, we will simplify right hand side of the inequality. Mod 5 root 7 plus 9i is equal to under root 5 root 7 square plus 9 square, and that is equal to under root 175 plus 81, and that is equal to under root 256, which is equal to 16. 16 can be written as 2 to power 4 or root 2 to power 8. So right hand side is log root 2 to power 8 to the base root 2. This power can be shifted here. So this is equal to 8 into log root 2 to the base root 2. This is in the form log a base a, which is equal to 1. So that is equal to 8. 8 can be written as 2 to power 3. So right hand side is simplified as 2 to power 3. Now let us see left hand side. Exponent of this whole. Now this can be shifted as power of 2. So this whole can be written as exponent of log 2 to power this to the base e, which is equal to 2 to power this whole. So 2 to power mod z plus 3 into mod z minus 1 upon mod z plus 1 is greater than or equal to 2 to power 3. On both the sides, base is same. So we can equate the exponents. Mod z plus 3 into mod z minus 1 upon mod z plus 1 is greater than or equal to 3. Now cross multiply. So it will be mod z plus 3 into mod z minus 1 is greater than or equal to 3 into mod z plus 1. Now take this to left hand side. So it will be mod z square minus mod z minus 6 is greater than or equal to 0. We can factorize this as mod z plus 2 into mod z minus 3 is greater than or equal to 0. Now this inequality is possible only when both are positive or both are negative. So we will consider two cases. In case 1, we will consider both of them to be positive. So mod z plus 2 is greater than or equal to 0 and mod z minus 3 is greater than or equal to 0. From this, mod z is greater than or equal to minus 2 and from this, mod z is greater than or equal to 3. If we combine both, we can say that mod z is greater than or equal to 3. In case 2, mod z plus 2 is less than or equal to 0 and mod z minus 3 is less than or equal to 0. If we combine both, we can say that mod z is less than or equal to minus 2, which is not correct, as we know that mod is always positive. So mod z should be greater than or equal to 0. So in this case, we will not get any solution. So finally, we can say that mod z is greater than or equal to 3. So minimum value of mod z will be equal to 3. So option A is correct. Ninth question, for a complex number z1, let Rez denote the real part of z. Let S be the set of all complex numbers z satisfying z to power 4 minus mod z to power 4 is equal to 4i z square, where I is equal to under root minus 1. Then the minimum possible value of mod z1 minus z2 square, where z1, z2 belong to S with real z1 greater than 0 and real z2 less than 0 is. This question was asked in JEE Advanced 2020. First, we will simplify z to power 4 minus mod z to power 4 is equal to 4i z square. Suppose z is equal to x plus iy. So z to power 4 is equal to x plus iy to the power 4. That gives x to power 4 plus y to power 4 minus 6x square y square plus I into 4x cube y minus 4xy cube. Mod z is equal to under root x square plus y square. So mod z to power 4 is equal to x square plus y square whole square, and that is equal to x to power 4 plus y to power 4 plus 2x square y square. 4iz square is equal to 4i into x plus iy whole square, and that is equal to 4i into x square minus y square plus 2i xy. Z to power 4 minus mod z to power 4 is equal to 4iz square gives minus 8x square y square plus I into 4x cube y minus 4xy cube is equal to minus 8xy plus I into 4x square minus 4y square. We will equate real part with real part and imaginary part with imaginary part. This gives xy is equal to 1. We have to calculate the minimum value of mod z1 minus z2 square. Suppose z1 is equal to x1 plus iy1 and z2 is equal to x2 plus iy2. So z1 minus z2 is equal to x1 minus x2 plus I into y1 minus y2. Mod z1 minus z2 square is equal to x1 minus x2 whole square plus y1 minus y2 whole square. From this relation, it is clear that if x is equal to 1, y is equal to 1. If x is equal to minus 1, y is also equal to minus 1. We will apply the same logic for x1, y1 and x2, y2. If x1 is equal to 1, then y1 is equal to 1. If x1 is equal to minus 1, then y1 is also equal to minus 1. Similarly, if x2 is equal to 1, y2 is equal to 1. If x2 is equal to minus 1, then y2 is also equal to minus 1. We have to consider real of z1 is greater than 0. That means x1 is greater than 0. And real of z2 is less than 0. That means x2 is less than 0. So x1 is greater than 0 and x2 is less than 0. x1 is greater than 0, so x1 is equal to 1 and y1 is equal to 1. And x2 is less than 0 means x2 is equal to minus 1 and y2 is equal to minus 1. So these are our desired values. We will put these values here. So we get x1 minus x2 whole square plus y1 minus y2 whole square as 1 minus minus 1 whole square plus 1 minus minus 1 whole square, and that is 2 square plus 2 square, or 4 plus 4, and that is 8. So our answer is 8. We will fill 8 here. Last question. Let S be the set of all complex numbers z satisfying mod z minus 2 plus I is greater than or equal to root 5. If the complex number z0 is such that 1 upon mod z0 minus 1 is the maximum of the set 1 upon mod z minus 1 such that z belongs to S, then the principal argument of 4 minus z0 minus z0 bar upon z0 minus z0 bar plus 2i is. These are the options given. This question was asked in JEE Advanced 2019. It is given that z satisfies mod z minus 2 plus I is greater than or equal to root 5. We can write this as mod z minus in bracket 2 minus I is greater than or equal to root 5. This matches with the standard form of the circle. We know that the standard form of the circle is mod z minus z0 is equal to r, where z0 is center and r is radius. Inequality greater than or equal to means z lies either on the circle or outside of the circle. Set S consists of all the elements which are of the form 1 upon mod z minus 1. So elements of S will be something like 1 upon mod z1 minus 1, 1 upon mod z2 minus 1, 1 upon mod z3 minus 1, and so on. We have to find the maximum value of 1 upon mod z minus 1. At maximum, z is equal to z0. So let us first simplify this. Suppose z is equal to x plus iy. So 1 upon mod z minus 1 is equal to 1 upon mod x plus iy minus 1. Or 1 upon mod z minus 1 is equal to 1 upon under root x minus 1 whole square plus y square. In this equation, on both the sides in numerator, it is 1. So maximum value of left hand side will occur when it is minimum value of the denominator of right hand side. So we can say that under root x minus 1 whole square plus y square should be minimum. We know that square of a real number is always positive. That means x minus 1 whole square is greater than or equal to 0 and y square is also greater than or equal to 0. So minimum value of x minus 1 whole square is equal to 0 and minimum value of y square is also equal to 0. So x minus 1 is equal to 0 and y is equal to 0, or x is equal to 1 and y is equal to 0. So we have got z0. So z0 is equal to x plus iy, and that is 1 plus 0i. So z0 is equal to 1 and z0 bar is also equal to 1. Now we have to find the principal argument of this. Here we will put z0 is equal to 1 and z0 bar is equal to 1. So argument of 4 minus z0 bar upon z0 minus z0 bar plus 2i comes out to be equal to argument of minus I. And we know argument of minus I is equal to minus pi by 2. So the correct option is option B. In next video, we will start chapter number 4, and that is quadratic equations. If you have a question, you can ask me on my Discord server. If you have not subscribed my channel yet, please do so.